What if the rules of reality as we know them are not as fixed as we once believed? For centuries, we've looked up at the night sky with a sense of familiarity, trusting that the laws of physics are universal and unchanging. But what if the universe itself is rewriting those rules right before our eyes? Recent discoveries in astronomy are revealing a cosmos far stranger, more mysterious, and more wonderfully chaotic than anything we could have imagined. And today, we're about to embark on a journey into the unknown. We'll explore 30 of the most bizarre, baffling, and breathtaking phenomena ever detected, objects and events so peculiar they defy explanation, challenging not only our understanding of space but the very foundations of science itself. Think about it, we live in an era where telescopes and satellites are capturing data at an unprecedented scale, and with every new observation, we're confronted with cosmic oddities that leave even the most brilliant minds questioning what is possible. From stars that behave in ways physics says they shouldn't, to mysterious structures that hint at forces beyond our current comprehension, these discoveries aren't just academic curiosities, they are glimpses into a reality that is wilder, more creative, and more humbling than we ever dreamed. This isn't science fiction, it's science in the making, unfolding in real time, and it invites all of us to reconsider our place in a universe that is still full of surprises. So settle in and open your mind to the extraordinary, because over the course of this video, we're going to dive deep into these 30 newly discovered space oddities, each one a story of curiosity, wonder, and the relentless human drive to understand the cosmos. Whether you're a lifelong stargazer or someone who simply loves a good mystery, there's something here that will captivate your imagination and maybe even change how you see the night sky. This is more than a list, it's an invitation to explore the edges of knowledge and witness firsthand the moments when science meets the sublime. First on our list is a phenomenon that sounds like it's ripped straight from the pages of a cosmic thriller, a dark matter hurricane currently sweeping through our very own solar system. This isn't a storm of wind and rain, but a silent, invisible tempest composed of the universe's most elusive substance. Astronomers have named it the S1 stream, and it's a vast river of dark matter particles, the remnants of a smaller galaxy that was torn apart and consumed by our Milky Way billions of years ago. This galactic debris is now passing through our corner of space at a staggering speed of about 500 kilometers per second, and while we can't see it or feel it, its presence is revealed through its subtle but undeniable gravitational influence. The detection of this stream is a masterpiece of indirect observation. Since dark matter doesn't emit, absorb, or reflect light, we have to look for the clues it leaves behind. Scientists used a technique called gravitational lensing, a fascinating consequence of Einstein's theory of relativity. Essentially, the immense gravity of the dark matter in the S1 stream acts like a lens, bending and distorting the light from distant galaxies behind it. By meticulously mapping these tiny distortions in the fabric of spacetime itself, researchers were able to trace the outline and velocity of this invisible current. It's like deducing the presence and shape of a powerful underwater current by watching how it makes the seaweed on the ocean floor sway. What makes this discovery so extraordinary is the unique opportunity it presents. For the first time, we have a concentrated, high-velocity flow of dark matter passing right through our neighborhood. This gives experiments designed to directly detect dark matter particles, like those conducted in deep underground laboratories, a significantly better chance of finally recording a signal. It's as if we've been trying to hear a faint, distant radio signal for decades with lots of static, and suddenly the broadcast tower has moved onto our street. This dark matter hurricane provides a natural laboratory, offering a potential shortcut to answering one of the biggest questions in all of physics. What is the true nature of the material that makes up roughly 85% of all the matter in the universe? Now, from an invisible storm of matter we can't see, we journey to a cosmic desert of nothingness so vast it defies logic. Our second oddity is the Eridanus Supervoid, a region of space that feels less like a part of our universe and more like a hole punched straight through it. Imagine a sphere of near-total emptiness nearly 1 billion light-years in diameter. To put that incomprehensible scale into perspective, if our Milky Way galaxy were the size of a grain of sand, this void would be larger than the entire Earth. Within this staggering volume of space, the expected population of hundreds of thousands of galaxies is almost entirely absent. It's not just a little underdense, it is a profound and unsettling nothingness that challenges our understanding of how the universe is structured. This void was discovered indirectly through its chilling effect on the oldest light in the universe, the cosmic microwave background. This ancient afterglow from the Big Bang is remarkably uniform, but it has a curious cold spot, and the Eridanus Supervoid is sitting right in front of it. The prevailing theory was that this immense emptiness could explain the cold spot through a phenomenon called the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels through such a vast void, it should lose a minuscule amount of energy as it fights against the weakening gravitational pull of all that missing matter, making it appear slightly cooler. But here's the twist: the sheer size and depth of the Eridanus Supervoid is so extreme that even this well-established cosmological effect can't fully account for the temperature drop we observe. The void is too empty and the spot is too cold. The numbers simply don't add up, leaving scientists with a magnificent puzzle. This discrepancy is what fuels truly spectacular theories. One compelling idea is that this supervoid isn't just a random fluctuation in the density of the universe, but a cosmic defect, a scar left over from the birth of spacetime itself. In the first fractions of a second after the Big Bang, the universe may have undergone a phase transition, much like water freezing into ice. And just as freezing water can trap bubbles of air, this cosmic freezing could have trapped a bubble of a different kind of vacuum, a region where the fundamental forces of nature settled into a different, more stable state, creating a pocket of literal nothingness that expanded to its staggering size. An even more mind-bending hypothesis suggests the void could be evidence of a collision with a parallel universe in the multiverse. The idea proposes that our universe is just one bubble in a vast cosmic foam of universes. If another universe bubble brushed against our own in the distant past, the interaction could have siphoned away matter and energy from the point of contact, leaving behind this unimaginably vast and empty wound in the fabric of our reality. While this remains highly speculative, the fact that such an idea is even entertained by serious cosmologists underscores just how extraordinary and inexplicable this great nothing truly is. It stands as a silent, cavernous reminder that for all we have learned, the cosmos is still capable of presenting us with mysteries of monumental proportions. This third discovery takes us from a void of missing matter to a galaxy that is overwhelmingly made of it. Meet Dragonfly 44, a galaxy that by all traditional measures simply shouldn't exist. It was found lurking in the relatively nearby Coma cluster, and at first glance it appears as little more than a faint, ghostly smudge of light. But when astronomers measured its mass, they were met with a result so baffling it sent ripples through the entire field of astrophysics. Dragonfly 44 possesses a mass virtually identical to that of our own Milky Way galaxy. The staggering implication is that this cosmic entity has the same gravitational heft as our home, which is filled with hundreds of billions of stars, enormous clouds of gas and dust, and a central supermassive black hole. Yet, when you look at Dragonfly 44, you see almost none of that. It contains only about 1% of the stars found in the Milky Way. The other 99% of its mass is completely invisible. This is a galaxy made almost entirely of dark matter. The identification of this dark galaxy was a painstaking process that relied on the motion of its few visible stars. By tracking the velocity and orbits of these stars, astronomers could calculate the total gravitational force holding them within the galaxy. The stars were moving far too quickly for the amount of visible mass present. If the gravity we could see from the stars and gas were the only force at work, those stars should have flown off into intergalactic space long ago. The only possible explanation is that they are being whirled around by the immense gravitational pull of a tremendous amount of matter we cannot see, a vast, sprawling halo of dark matter that makes this object not a failed galaxy, but a triumph of dark matter, a cosmic entity where the invisible framework has built a structure without populating it with the bright cities of stars we expect. The existence of Dragonfly 44 and other similar ultra-diffuse galaxies poses a profound challenge to our models of how galaxies form. The prevailing theory, the cold dark matter model, suggests that galaxies begin their lives within halos of dark matter. The gravity of this dark matter pulls in ordinary matter, which eventually cools, condenses, and forms stars. Dragonfly 44 clearly has the dark matter halo, but for some mysterious reason, the star formation process almost completely failed. Perhaps the gas within its halo was stripped away early on by the gravitational tides of other galaxies in the dense Coma cluster, preventing it from ever coalescing into stars. Or maybe the gas was too hot or too turbulent to cool down effectively, stalling the entire stellar production line. But the deeper mystery is what such a galaxy means for the nature of dark matter itself. Some alternative theories of gravity, like modified Newtonian dynamics or MOND, were proposed to explain galactic rotations without the need for dark matter. However, the extreme discrepancy in Dragonfly 44, a Milky Way-sized mass with almost no stars, is incredibly difficult for MOND to explain, as the theory tweaks the visible mass to account for the gravity. Here, there is almost no visible mass to tweak, making this ghostly galaxy one of the strongest pieces of evidence, yet that dark matter is not a modification of gravity, but a real, physical substance that can structure the universe all on its own. It forces us to ask, are there far more of these dark galaxies out there, invisible to our telescopes, constituting the true hidden backbone of the cosmos? Dragonfly 44 is not just an oddity, it is a silent revolution, a galaxy that speaks volumes about the unseen forces that truly govern the universe. Our next cosmic enigma takes us from the shadowy realms of dark matter to the heart of a stellar cataclysm so extreme it warps the very laws of physics. This is the story of a magnetar, a neutron star with a magnetic field of such incomprehensible power that it earns the title of a true magnetic monster. To grasp the sheer intensity of this object, try to conceive of a magnetic force so potent that if you were to approach within 1,000 kilometers of it, the field would literally pull the iron from your blood. It could, from a distance of halfway across our galaxy, effortlessly erase the magnetic strip of every credit card on Earth. This isn't just a strong magnet. It is a fundamental force of nature unleashed, an entity that exists at the very edge of what our current physics says is even possible. Neutron stars themselves are already the stuff of legend, the collapsed, ultra-dense cores of what were once massive stars, cramming more mass than our Sun into a sphere no wider than a city. But a magnetar is a neutron star that has undergone a further transformation, becoming something even more exotic and terrifying. The magnetic field of a typical magnetar can be 1,000 trillion times more powerful than Earth's protective magnetic shield. The one we're discussing was discovered through its frantic and deadly energy releases. Unlike the steady glow of a normal star, this object announces its presence with violent, random eruptions of high-energy X-rays and gamma rays, flashes of radiation so bright they can temporarily blind telescopes across the solar system. It's a celestial beacon not of light but of raw, destructive power. The origins of such an extreme object are as violent as its nature. Most astrophysicists believe magnetars are born in the supernova deaths of the most massive and rapidly spinning stars. The key ingredient is a perfect, terrifying storm of conditions during the collapse. As the star's core implodes, it conserves the original star's intense magnetic field, squeezing those magnetic lines into an infinitesimally small volume, which amplifies their strength to these monstrous levels. Simultaneously, the infant neutron star is thought to be spinning at a dizzying rate, hundreds of times per second. This rapid rotation, acting on its interior of superfluid neutrons, functions like a colossal dynamo, generating even more magnetic energy and creating a feedback loop that pushes its field strength into this record-breaking regime. What truly captivates scientists, however, is what this magnetic monster implies about the fabric of reality. At these unimaginable field strengths, something known as the quantum electrodynamic limit is approached. This is a theoretical boundary where the magnetic field becomes so powerful it can actually alter the vacuum of empty space itself. In a vacuum under normal conditions, particle-antiparticle pairs constantly flicker in and out of existence. But under the influence of a magnetar strength field, this quantum foam is polarized and distorted, effectively creating a new state of matter. The physics in this environment are so extreme that they are impossible to replicate in any laboratory on Earth, making the magnetar a unique natural experiment for testing the limits of our most fundamental theories. It forces us to ask, at what point does our understanding of magnetism and matter itself break down? This magnetic monster isn't just a curiosity. It is a cosmic extreme, a laboratory at the edge of physics, showing us just how strange and powerful the universe can become when it pushes its own rules to the absolute limit. If the idea of a magnetic monster pushes the limits of physics, our fifth oddity redefines the meaning of cosmic velocity and violence. Picture a supermassive black hole, an object with the mass of 20 million suns, not sitting serenely at the heart of a galaxy as every model predicts, but instead being violently ejected and sent careening through the darkness of intergalactic space. This isn't a slow drift, it's a runaway behemoth traveling at staggering speeds, and in its wake it isn't leaving destruction, but a breathtaking trail of newborn stars, a contrail of creation marking its path through the void. This incredible discovery began with a streak of light that defied all expectations. Astronomers using the Hubble Space Telescope were studying a distant galaxy when they noticed a perfectly linear, brilliant streak extending from its core. At first, it was assumed to be an imaging artifact or perhaps a cosmic ray scratch on the sensor, but further analysis revealed it was something far more real and far more spectacular. The streak was not a flaw, but a chain of young, massive blue stars, a stellar umbilical cord connecting the galaxy to the rogue black hole that had fled from it. The black hole itself, invisible as all black holes are, was revealed by the intense radiation blazing from the gas immediately around it, a brilliant beacon preceding this starry trail. The physics behind this cosmic expulsion are as violent as they are elegant, a story written in the language of gravity waves. The most plausible scenario is a galactic merger, a slow-motion collision between two galaxies, each with its own central supermassive black hole. As the galaxies intertwined, their black holes would have begun a gravitational dance, spiraling inward toward a common center. In the final moments before they merged, they would have emitted tremendous ripples in space-time known as gravitational waves. If the merger was asymmetrical, if the two black holes were of very different masses, or if their final spins were misaligned, the resulting gravitational wave blast could have been shot out in one preferred direction, like the recoil from a cannon. This recoil effect would have been powerful enough to kick the newly formed, larger black hole clear out of the galactic core, sending it flying into the great beyond at speeds exceeding 5 million miles per hour. What makes this phenomenon truly poetic is the trail of stars it leaves behind. As the black hole plows through the tenuous gas that exists between galaxies, it doesn't just push it aside. The immense gravitational forces and the shock of its passage actually compress that gas, triggering the very conditions needed for star formation. The black hole acts as a chaotic midwife, forcibly gathering the raw material of the universe and crushing it into new suns. These aren't the orderly, ancient stars of a galactic disk. They are a forced, frantic generation of youth, a desperate spark of light in the absolute darkness, all born from the chaotic flight of the ultimate dark engine. This observation provides the first tangible evidence for a long-theorized but never-seen population of wandering or rogue black holes that could be drifting unseen throughout the universe. It also solves another mystery, the existence of hyper-compact star clusters found in the empty spaces between galaxies. Some of these isolated clusters may very well be the faded, aging remnants of such stellar trails, long after their creator black hole has moved on. The discovery of this runaway giant forces us to reconsider the life cycle of galaxies. It shows that the central engines of galaxies are not always fixed anchors. They can be temporary residents, capable of being torn from their homes by the most cataclysmic events the universe can muster, forever changing the destiny of the galaxy left behind. While we've seen how immense voids can leave a cold imprint on the cosmos, our sixth oddity presents a chill of a far more profound and controversial nature. This is the mystery of the Great Cold Spot, a vast and perplexing region within the cosmic microwave background that is significantly colder than it should be. The cosmic microwave background is the oldest light we can observe, a faint afterglow from the Big Bang that fills the entire sky. It is remarkably uniform, a thermal snapshot of the infant universe, but it is not perfectly smooth. There are tiny, random fluctuations in temperature, variations on the scale of 1 part in 100,000, which are the seeds from which all galaxies and clusters eventually grew. The Great Cold Spot, however, is different. It is a large, coherent patch of sky about 5 degrees across 10 times the diameter of a full moon that is noticeably and anomalously cold. It's not just a statistical fluke, it's a feature that stubbornly refuses to be explained by our standard model of cosmology. Initial attempts to understand this cold spot pointed toward a phenomenon we just explored, a supervoid. The logic was compellingly simple. If a vast, mostly empty region of space lies between us and the cosmic microwave background, the light passing through it would undergo a subtle transformation. As a photon of this ancient light enters the void, it must climb out of the gravitational well created by the matter at the void's edge. Since the universe has expanded and the well has become shallower by the time the photon exits, it actually gains a bit more energy climbing out than it lost falling in. This net gain translates to a very slight warming of the light. However, this entire process is framed within the expanding universe, and that expansion adds another effect. The overall growth of space causes the photon to lose energy, and this loss dominates, resulting in a net cooling of the light. This is the integrated Sachs-Wolf effect. So, a giant void could, in theory, make the cosmic microwave background behind it appear colder. Astronomers scoured the region and indeed found the Eridanus Supervoid, a significant underdensity of galaxies. But there was a devastating problem. The void is far too small and not nearly empty enough to account for the severe temperature drop observed in the Great Cold Spot. The numbers were off by a factor of nearly 10. The void might contribute to the chill, but it cannot be the sole cause. The cold spot remains largely unexplained. This failure of a conventional explanation is what opens the door to truly spectacular possibilities, and one of the most thrilling is the multiverse hypothesis. Some cosmologists propose that the Great Cold Spot is not a feature of our universe at all, but a cosmic bruise, an imprint from a collision with another universe in the multiverse. The theory suggests that our universe is just one expanding bubble in a vast, frothing meta-universe where countless other bubble universes are constantly inflating into existence. If another bubble universe had collided with ours in the distant past, the energy released at the boundary of that collision would have left a distinct signature on the cosmic microwave background. The interaction would have drained energy from that region of space, creating a large circular anomaly of lower temperature, exactly like the cold spot we observe. In this radical interpretation, we are not looking at a random fluctuation or a shadow cast by a void, but tangible, observational evidence that our universe is not alone. Of course, such an extraordinary claim faces intense scrutiny and alternative proposals. Other physicists suggest the cold spot could be the result of a cosmic texture. This idea comes from theories of grand unification, which propose that as the early universe cooled, the fundamental forces may have undergone phase transitions that did not play out perfectly smoothly. Much like imperfections forming in crystal structures or wrinkles in a fabric, topological defects could have formed in the very geometry of spacetime. A cosmic texture is one such hypothetical defect, a knot of concentrated energy that would have a specific gravitational footprint, one that could potentially create a cold spot of the exact size and temperature profile we see. While this idea is less sensational than a collision with another universe, it is no less profound, as it would provide direct evidence for physics at energy scales trillions of times higher than what we can achieve in particle colliders, offering a window into the forces that shaped existence in its first fleeting moments. The Great Cold Spot, therefore, is more than just a curiosity on a map of the sky. It is a focal point for a fundamental debate about the nature of reality itself. Is it a simple, if unusually large, void whose properties we have miscalculated? Is it a fossil from the asymmetric birth of the cosmos, a texture frozen into the fabric of spacetime? Or is it the first empirical clue that we inhabit a multiverse, a single bubble in an infinite ocean of other realities? Its enduring mystery reminds us that even our most comprehensive maps of the universe still contain regions marked "Here be dragons," challenging us to look deeper and question broader. This cold patch is a question written in the faintest light of creation, and its answer could rewrite not only our cosmology textbooks but our very understanding of existence. From the grand, theoretical chill of the Great Cold Spot, we now turn our gaze to an object of stunning and precise beauty, a celestial structure so geometrically perfect it seems to have been drafted by a cosmic architect. This is the Red Rectangle Nebula, a phenomenon that encircles a dying star and presents us with one of the most visually arresting and physically baffling sights in the entire night sky. Its name, while descriptive, hardly does it justice. Through the lens of powerful telescopes, it doesn't appear as a fuzzy cloud or a ragged shell, as most planetary nebulae do. Instead, it reveals itself as a series of near-perfect concentric rectangular rungs, like a ladder thrown across space, with a brilliant, dark, rifted X-shape running through its core. This is not the chaotic, explosive death we typically associate with stars. It is a structured, almost orderly dissolution, and its existence challenges our understanding of the final chapters of a star's life. The story of the Red Rectangle begins with its central star system, known as HD 44179. This isn't a single star but a binary pair, two stars locked in a tight orbital dance. One of these stars has exhausted the nuclear fuel in its core and has swollen into a red giant, casting off its outer layers into space. Its companion, a smaller white dwarf star, orbits closely enough to drastically influence how this material is ejected. This binary interaction is the key to the nebula's unique shape, but the precise mechanics that create such sharp, linear symmetry, rather than the more common spherical or bipolar outflows, have been a subject of intense debate for decades. The prevailing theory is a masterpiece of celestial precision and timing. As the red giant star puffs away its atmosphere, the powerful gravitational field and stellar wind from its white dwarf companion act like a sculpting tool, funneling the expelled gas and dust into two opposing cones, their narrow ends meeting at the central star system. From our vantage point on Earth, we are looking directly down the barrel of one of these cones. The edges of the cone, which would normally appear circular, are seen in projection as the two long, straight lines forming the top and bottom of the X. But this alone doesn't explain the rungs of the ladder, the series of concentric rectangles. Those are believed to be the work of episodic eruptions. The dying star isn't shedding its skin in a continuous, smooth flow, but in a series of fits and starts like a geyser with a regular eruption cycle. Each pulse of material expands outward until it hits the slower moving gas from the previous eruption, creating a standing shock wave that lights up as a distinct, sharp-edged rung. The result is a structure that resembles a spinning top viewed from the side, with its concentric rings of ejected material. However, the true, deep mystery of the red rectangle isn't just its shape, but the bizarre composition of the dust within it. This nebula is one of the richest known sources of a class of complex organic molecules called polycyclic aromatic hydrocarbons. These are intricate, carbon-based molecules that are considered fundamental building blocks of life as we know it. In the red rectangle, the conditions are so peculiar and the radiation from the central stars is so precisely tuned that these molecules are fluorescing, glowing with a deep, rich red hue that gives the nebula its common name. This has led some scientists to speculate that we might be witnessing a cosmic factory for probiotic chemistry, a place where the raw ingredients for life are being forged in the aftermath of a stellar death. The profound implication is that this geometric marvel might be more than just a pretty picture. It could be a crucial link in the chain of cosmic evolution, demonstrating how the death of one generation of stars can seed the universe with the complex compounds necessary for the birth of the next. The Red Rectangle Nebula stands as a stunning testament to the fact that even in death, the universe operates with an underlying order and a creative potential that we are only beginning to understand. It is a reminder that the cosmos is not only stranger than we imagine, but often more beautiful and more structured, hiding its deepest secrets within forms of breathtaking symmetry. Our journey now takes us to a star that became a global sensation, not for what it is, but for what it seemed to be doing. This is the story of KIC 8462852, better known as Tabby's star, or the star that made us all wonder, if only for a moment, if we were not alone in building a civilization. Discovered by citizen scientists in the Kepler mission data, this otherwise ordinary star, slightly larger and hotter than our Sun, displayed a pattern of dimming unlike anything ever witnessed. Stars dip in brightness all the time, usually because a planet is transiting across their face. These dips are small, predictable, and periodic. Tabby's star was different. Its light curves were chaos. There were sudden, precipitous drops in brightness of up to 22%, an amount that would require an object many times the size of the star itself to block the light, and these dips lasted for days or weeks at a time. Even more bizarrely, the long-term data showed a century-long, steady, and inexplicable overall dimming of the star. It was as if something was not just passing in front of the star, but steadily dismantling it. The most tantalizing and admittedly sensational explanation was the one that captured the public's imagination: an alien megastructure. Specifically, the theory pointed to a Dyson sphere, a hypothetical swarm of energy collecting satellites or panels constructed by an advanced civilization to harness the entire power output of its sun. Such a vast, irregular array of objects would perfectly explain the wild, aperiodic dimming patterns. For a brief, glorious period, we were allowed to dream that we might have stumbled upon evidence of intelligence on a scale beyond our comprehension. But science, in its diligent and methodical way, began to search for more natural, if no less extraordinary, explanations. The latest findings from intensive observation campaigns have largely, though not completely, shifted the consensus away from aliens and toward cosmic dust. Detailed spectroscopic analysis during the dimming events has been crucial. When a solid object like a planet or a megastructure passes in front of a star, it blocks all wavelengths of light equally. However, when the obscuring material is made of tiny dust particles, it scatters and blocks shorter wavelengths of light, like blue and ultraviolet, more effectively than longer, redder wavelengths. This is precisely what telescopes observed at Tabby's star. The dimming was more pronounced in blue light than in red light. This is the telltale signature of dust, not opaque solid objects. The current leading theory suggests a vast, uneven cloud of fine dust particles, possibly from a catastrophic collision in the star's system, is responsible for the major dimming events. But what could create such an immense and chaotic cloud of debris? One compelling hypothesis points to the destruction of an exomoon. Imagine a gas giant planet, similar to Jupiter, migrating inward from the cold outer regions of its system toward its host star. As it draws closer, the immense tidal forces from the star could rip apart a large moon orbiting the gas giant, shattering it into billions of fragments. This would create a gigantic, swirling cloud of dust and rubble that would trail the planet in its orbit. The irregular shape of this cloud and the precession of its orbit over time could account for the bizarre, unpredictable dimming patterns we detect. The long-term secular dimming could then be explained by a vast ring system around the planet or a dispersal of the finest dust grains throughout the stellar system, creating a permanent, thin haze. Yet, for all the progress, the mystery is far from definitively solved. The dust explanation is compelling, but it still has to account for the sheer extreme depth of the dimming events and the star's long-term fading with a level of precision that current models are still working to achieve. The door, while now only slightly ajar, has not been completely closed on more exotic possibilities. Some researchers still argue that even within the dust model, there could be an artificial origin. Perhaps the dust is the byproduct of massive-scale industrial activity or the debris from a dismantled planet. While this remains a fringe view, the enduring enigma of Tabby's star serves a purpose far greater than just solving one astronomical puzzle. It taught the scientific community and the public a valuable lesson in how to conduct the search for extraterrestrial intelligence, or SETI. It showed that we now have the tools to look for technosignatures, the signs of advanced technology, and that we must follow the evidence wherever it leads, whether to a cloud of dust or, one day, to something that truly changes our place in the universe. Tabby's star remains a beacon of curiosity, a reminder that sometimes the most exciting answer is not a definitive solution, but a deeper, more complex question. While our previous oddities involved things we can see or infer through gravity, our ninth discovery reminds us that some of the universe's most dramatic messages arrive in the form of nearly nothing at all. This is the story of the ghost particle, a single ultra-high-energy neutrino detected deep within the Antarctic ice that opened an entirely new window onto the cosmos. To understand why this one tiny particle caused such a massive stir in the world of astronomy, you have to appreciate the nature of the neutrino itself. Neutrinos are among the most abundant particles in the universe, yet they are famously aloof and incredibly difficult to detect. They have no electric charge and almost no mass, which allows them to travel for billions of light years in a perfectly straight line, passing through entire planets and stars as if they weren't even there. Trillions of them are zipping through your body every second, completely unnoticed. Catching one, especially one with a specific known origin, is like identifying a single specific drop of water in a hurricane. The detector that achieved this near miracle is as extraordinary as the particle it caught. The Ice Cube Neutrino Observatory isn't a traditional telescope with a lens and a mirror. It's a colossal cube of incredibly pure Antarctic ice, 1 kilometer on each side, instrumented with over 5,000 ultra-sensitive optical sensors buried more than a mile beneath the surface. Scientists use this immense volume of ice as a target. On the exceedingly rare occasion that a high-energy neutrino does interact with an atom in the ice, it creates a secondary particle that moves faster than the speed of light in that medium. This generates a faint shockwave of blue light known as Cherenkov radiation, which the buried sensors can detect. By analyzing the timing and intensity of this faint blue glow, physicists can trace the neutrino's path back to its origin point in the sky with astonishing precision. On September 22, 2017, the IceCube sensors recorded an event that would change astronomy. A single neutrino with an energy over 200 times that of the protons accelerated in the Large Hadron Collider slammed into the ice. This wasn't just any neutrino, it was a cosmic messenger of the highest order, a particle with enough energy to have come from the most violent engine in the universe. Within seconds of the detection, automated alerts were sent out to observatories around the globe and in space. Telescopes of every kind swiveled to look in the direction from which the neutrino had come. Their search revealed something spectacular. A blazar known as TXS0506+056 was in a state of extreme outburst. A blazar is one of the most energetic objects in existence, a supermassive black hole at the heart of a distant galaxy that is actively feeding on surrounding matter. As material spirals into the black hole, immense magnetic fields funnel some of it away in two powerful jets of radiation and atomic particles shooting out from the poles at nearly the speed of light. We just happen to be looking directly down the barrel of one of these jets, putting us in the direct line of fire from a cosmic particle accelerator of unimaginable power. The correlation was undeniable. This blazar, located over 4 billion light-years away, was the source of the neutrino. For the first time in history, we had definitively pinpointed a source of high-energy cosmic neutrinos and also identified a blazar as a source of these ghostly particles. This single detection marked the dawn of a new field, neutrino astronomy. Before this, our view of the universe's high-energy phenomena was based entirely on electromagnetic radiation, light, X-rays, gamma rays. But light can be obscured or scattered by cosmic dust and magnetic fields. Neutrinos, being ghostly and indifferent to matter, travel unimpeded, delivering pure, uncontaminated information straight from the heart of the most extreme events. This event proved that we can now use them as direct probes, allowing us to see into environments that were previously completely opaque, like the chaotic regions immediately surrounding the supermassive black holes at the centers of active galaxies. The implications of this are profound. We now have a powerful new tool to study the accelerators of cosmic rays, high-energy protons and atomic nuclei that constantly bombard our atmosphere. For over a century, the origin of the most energetic of these cosmic rays has been one of the biggest mysteries in physics. We knew they came from somewhere outside our galaxy, but we could never track them back to their source because their paths are bent and scrambled by magnetic fields on their journey. Neutrinos are the smoking gun. They are created in the same violent processes that produce cosmic rays, and because they travel in straight lines, they point directly back to their source. This one ghost particle did more than just solve a mystery. It inaugurated an entirely new way of seeing the universe, transforming these elusive phantoms from objects of pure physics into beacons that guide us to the cosmos's most spectacular and violent engines. For decades, cosmology was haunted by a deeply embarrassing problem, one that struck at the very heart of our inventory of the universe. We could account for the dark matter and dark energy, but we couldn't even find all the ordinary matter, the stuff you, me, the stars, and all the planets are made of. This is baryonic matter, the protons and neutrons that constitute every atom in existence. When astronomers added up all the visible material they could see in galaxies, stars, and gas clouds, and then compared it to the total amount of ordinary matter predicted to exist by our rock-solid models of the Big Bang, based on the cosmic microwave background, the numbers didn't just disagree, they were catastrophically off. Nearly half of all the atoms in the universe were simply missing. This wasn't exotic dark matter, this was the very stuff of us, and it had vanished without a trace. It was the universe's most frustrating game of hide and seek, and for years we were utterly losing. The solution to this cosmic mystery wasn't found in some distant, exotic object, but in the seemingly empty spaces between the galaxies. Astronomers had long theorized that the missing matter might be hidden in a vast, diffuse web of extremely hot gas, a structure known as the warm-hot intergalactic medium, or WIM. This wouldn't be a cloud in any traditional sense. It would be a superheated plasma, a thin soup of protons and electrons with temperatures ranging from hundreds of thousands to millions of degrees Celsius, so tenuous that a single cubic meter of it might contain only a handful of particles. The challenge was monumental. How do you see a cloud of gas that is both incredibly hot and incredibly sparse, spread across billions of light years of nothingness? Its extreme temperature means it doesn't emit visible light, and its low density means it emits very little of anything else. It is the epitome of a cosmic ghost. The breakthrough came from a clever and indirect technique, a form of cosmic cartography that used the brightest beacons in the universe as flashlights. When a distant quasar, a galaxy with a brilliantly shining active black hole at its center, sends its light on a multi-billion-year journey toward Earth, that light passes through the otherwise invisible filaments of the WIM. The specific atoms within this hot gas, primarily highly ionized oxygen, act like a chemical filter. They absorb very specific wavelengths of the quasar's ultraviolet light, leaving behind a unique but incredibly faint fingerprint in the quasar's spectrum. Finding this signature is like trying to spot the ghostly imprint of a single specific moth on the glass of a lighthouse lens from 1,000 miles away. It required the most sensitive space-based ultraviolet telescopes like the Hubble Space Telescope to finally detect these telltale absorption lines, proving that the WIM was not just theoretical but real, and it was everywhere. Further confirmation arrived from an entirely different angle, using the most massive structures in the universe, galaxy clusters. As galaxies fall into these immense gravitational wells, they pull and compress the WIM filaments that connect them. This process heats the gas to even more extreme temperatures, causing it to glow not in visible light, but in low-energy X-rays. Space observatories like NASA's Chandra X-ray Observatory and Europe's XMM Newton were tasked with staring at the spaces between the bright galaxies in large-scale cosmic structures. After painstakingly long exposures, they managed to capture a faint, pervasive X-ray glow emanating from these empty voids, the direct emission from the warmed and compressed WIM. It was the equivalent of turning out all the lights in a city and finally seeing the faint, glowing fog that had been there all along. The discovery of the WIM solved one of astronomy's most persistent puzzles, closing the book on the missing baryon problem. It revealed that the universe's structure is not just defined by the glittering cities of galaxies, but by the sprawling, invisible infrastructure that connects them. This web of hot gas is the cosmic highway system along which galaxies travel and the reservoir from which they formed. It contains more ordinary matter than all the stars and galaxies combined, meaning the true architecture of the cosmos is not what shines in the darkness but what hides within it. This finding completes our census of the universe's contents, confirming that our fundamental theories about the Big Bang were correct all along. We just needed to develop the tools and the patience to see where all the atoms were hiding. The WIM is the final piece of the ordinary matter puzzle, a reminder that even the void is teeming with structure if only we know how to look. Moving from the grand cosmic web to a solitary traveler, our 11th oddity presents an object so strange it arrived from beyond our solar system, only to leave us with more questions than answers. This is the story of Oumuamua, the first confirmed interstellar object ever detected passing through our cosmic neighborhood. Its Hawaiian name, meaning "a messenger from afar arriving first," was poetic, but nothing could prepare scientists for the profound mystery this silent scout would deliver. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii, it was immediately clear this was no ordinary asteroid or comet from our own system. Its hyperbolic orbit and staggering speed of nearly 94,000 kilometers per hour announced its extragalactic origin, a visitor from the vast ocean of space between the stars. Yet its true nature only grew more baffling the closer we looked. The first surprise was its shape. Based on the extreme variations in its brightness as it tumbled through space, astronomers deduced that Oumuamua is highly elongated, likely shaped like a cigar or a pancake, with its length estimated to be up to 10 times greater than its width. In a solar system where most asteroids and comets are roughly spherical or lumpy potatoes, this was bizarrely unusual, but the real shock came months after its discovery, as it was already speeding away from the Sun. Careful analysis of its trajectory revealed it was experiencing a tiny but persistent non-gravitational acceleration. In other words, it was moving slightly faster than could be explained by the gravitational pull of the Sun and planets alone. Something was giving it an extra push. For comets, this is common. Heat from the Sun vaporizes their icy surfaces, creating jets of gas that act like natural rocket engines. The critical problem with Oumuamua was that it showed no visible signs of this cometary activity, no surrounding cloud of gas and dust, no visible tail. It was, to all appearances, a completely inert, rocky object, yet it was behaving like a comet with its engines firing. The scientific community was electrified, and a frantic search for explanations began. One of the leading natural explanations posits that Oumuamua could be a hydrogen iceberg. The theory suggests it formed in the cold, dense core of a giant molecular cloud, where temperatures are just a few degrees above absolute zero. In such an environment, solid molecular hydrogen could accumulate into a large body. As this hydrogen iceberg approached the Sun, the solar radiation would have caused the frozen hydrogen on its surface to sublimate, turning directly from a solid into a gas. Because hydrogen gas is invisible to our telescopes, this would explain the observed acceleration without any visible coma or tail. However, many physicists are skeptical, questioning whether a hydrogen iceberg could survive a journey of millions of years through interstellar space without being evaporated by the faint background radiation that fills the galaxy. Another compelling natural theory is that Oumuamua is a nitrogen iceberg, a chunk broken off from the surface of a Pluto-like exoplanet in another star system. This would be remarkably resilient, and the sublimation of nitrogen could also provide the necessary thrust while remaining largely undetectable. Yet, the amount of nitrogen required to form such a large object would be staggering, implying that its parent system must have been rich with such material, a possibility that pushes the boundaries of what we believe is typical in planetary formation. Of course, the most sensational hypothesis, famously proposed by Harvard astronomer Avi Loeb, is that the object's acceleration could be explained by radiation pressure from sunlight. For this to work, Oumuamua would need to be extremely thin and lightweight, a solar sail, a piece of alien technology. A light sail of natural origin is almost unimaginable, but one crafted by an intelligent civilization could use the tiny pressure from photons of light for propulsion, exactly matching the acceleration profile we observed without the need for any visible outgassing. This idea, while captivating, is considered highly speculative by the majority of the astronomical community, who argue that we must exhaust all natural explanations before invoking such extraordinary possibilities. The central frustration is that we discovered Oumuamua too late, as it was already on its way out of the solar system. We had only a few weeks to gather data with the world's most powerful telescopes before it became too faint to observe, forever vanishing into the darkness from whence it came. This lack of definitive data is what seals Oumuamua's status as a profound and enduring puzzle. It was a one-of-a-kind event that passed us by before we could truly understand it. Its legacy, however, is immense. It single-handedly created a new branch of astronomy, the study of interstellar objects. Its visit was a statistical fluke that proved our solar system is constantly being visited by debris from other stars, We had simply never built telescopes powerful enough to detect these fleeting guests before. Now, astronomers are preparing for the next one, designing missions that could be launched at a moment's notice to rendezvous with and study a future interstellar visitor up close. Oumuamua was our first glimpse into the building blocks of other star systems, a piece of a distant world that traveled for eons to briefly grace our skies. Whether it was an exotic iceberg or something even more incredible, its true nature remains locked within its silent, tumbling form, a cosmic secret carried away into the void. Leaving behind the solitary mystery of Oumuamua, we now journey to the very dawn of time to confront a discovery that fundamentally challenges our story of how the universe grew up. This is the story of an ancient galaxy so massive and so mature that its very existence seems to break the rules of cosmic evolution. Designated GNZ11, this galaxy was spotted by the Hubble Space Telescope as a faint red smudge of light, a view that encompassed a staggering 11 billion years of travel time. We are seeing it as it was when the universe was a mere toddler, only about 1.5 billion years old. In human terms, that's like looking at a photograph of a 3-year-old child who is not only fully grown but has already built a thriving, complex civilization. The galaxy's red color was the first clue to its impossible nature. In astronomy, red typically signifies age, indicating a population of older, cooler stars. This was completely counter to expectations for such an early epoch, when the universe should have been filled with the blue light of hot, young, newly forming stars. The shock deepened when follow-up observations with more powerful telescopes, like the Spitzer Space Observatory, were able to measure its mass. The findings were nothing short of astonishing. GNZ11 was estimated to contain over 100 billion suns, making it as massive as our present-day Milky Way galaxy. This presented cosmologists with a monumental puzzle. According to our most successful models of galaxy formation, the cold dark matter model with a cosmological constant, the early universe simply did not have enough time to assemble such a behemoth. After the Big Bang, the cosmos needed time to cool, for the first stars to ignite, for those stars to congregate into small proto-galaxies, and for those building blocks to then slowly merge together over billions of years through gravitational attraction to form the large galaxies we see today. The presence of a fully formed Milky Way-sized galaxy at such an early date suggests this entire process happened at a breakneck speed, compressing a timeline of billions of years into just a few hundred million. It's as if we found a complete modern city built in a decade when our history books insist it should have taken a century. So how could such a galaxy form so quickly? Astronomers are now forced to consider that the earliest stages of the universe were far more efficient and energetic than we ever imagined. One compelling theory suggests that the seeds for these giant galaxies were not small proto-galaxies, but incredibly dense and massive clumps of dark matter that collapsed immediately after the Big Bang. Within these rare, ultra-dense regions, the ordinary matter, the gas that forms stars could have fallen in at an extraordinarily rapid rate, leading to a ferocious and short-lived burst of star formation known as a starburst. In this scenario, GNZ11 didn't form slowly and methodically. It experienced a single, violent, and incredibly productive growth spurt, burning through its cosmic fuel supply in a frenzy of stellar creation to become a cosmic titan in record time. The implications of this discovery ripple far beyond this one galaxy. If GNZ11 is not a bizarre one-off anomaly but a representative of a larger, yet-to-be-discovered population of ancient giants, it means our entire timeline for cosmic structure formation is flawed and needs a significant revision. Our models might be missing a key piece of physics that allowed matter to clump together much faster in the early universe. Perhaps dark matter interacts with itself in ways we haven't accounted for, or maybe the primordial gas was able to cool and collapse more efficiently than our simulations allow. Finding more of these impossible galaxies is now a primary goal for the James Webb Space Telescope, whose powerful infrared eyes are perfectly suited to peer back into this epoch and conduct a proper census. Each new discovery will either force us to rewrite the textbooks on galaxy evolution or lead us to an even deeper understanding of the exotic physics that govern the universe's frantic and spectacular youth. GNZ11 stands as a silent, ancient sentinel, a massive question mark written in starlight that forces us to reconsider how quickly the cosmos can wake up and get to work. After the silent, enigmatic passage of an interstellar visitor, we now turn to a phenomenon that is anything but silent, a rhythm, a pulse, a steady cosmic drumbeat emerging from one of the universe's most destructive places. Our 13th oddity is the heartbeat of a black hole, a mysterious, repeating signal that offers a stunning glimpse into the violent, yet strangely orderly process of cosmic consumption. Discovered in a system where a black hole is locked in a gravitational dance with a companion star, this isn't a random explosion of energy. It's a precise, periodic pulse of X-rays that beats with the regularity of a metronome, echoing across thousands of light years. To find such a predictable rhythm in the chaotic swirl of matter just outside the point of no return is like finding a perfectly ticking clock in the heart of a hurricane. This incredible signal was detected emanating from a black hole binary system, where a stellar mass black hole is actively stripping material away from its orbiting stellar partner. As this stolen gas spirals inward, it doesn't fall directly into the black hole. Instead, it forms a vast, flat structure known as an accretion disk, a whirlpool of superheated plasma circling the abyss at nearly the speed of light. It is from the inner edge of this furious maelstrom, just milliseconds away from the event horizon, that the heartbeat originates. The pulse itself is a flash of high-energy X-rays that repeats every few seconds or minutes, a cycle that can remain stable for years at a time before suddenly vanishing, only to reappear later. This persistence is what makes it so extraordinary. It's a stable structure in an environment of unimaginable violence. So what physical process could possibly create such a dependable rhythm in this realm of chaos? Astrophysicists believe the heartbeat is a sign of a fundamental state change in the accretion disk itself, a switch between two modes of feeding. In the standard mode, the inner region of the disk is incredibly hot and puffy, like a donut swollen with energy. In this state, it is optically thick, meaning the radiation produced deep within it struggles to escape, leading to a steady, bright glow. But as more and more material piles up from the companion star, the pressure and density in this inner region reach a critical tipping point. The entire structure suddenly collapses, condensing into a dense, cool, and incredibly thin sheet. In this new state, it becomes optically thin, allowing the intense radiation from the very innermost stable orbit to blast outward unimpeded. This sudden release of pent-up energy is the heartbeat, the brilliant X-ray flash we detect. The collapse then allows material to rush inward more efficiently, draining the inner disk and causing it to heat up and puff out again, restarting the entire cycle. This creates a self-regulating feedback loop: accumulation, collapse, eruption, and recharge. The entire process is a delicate cosmic balancing act between the inward pull of gravity and the outward pressure of radiation. The stable period of the heartbeat is essentially a direct measurement of how long it takes for the inner disk to fill up to its breaking point. It's a natural timer, giving us an unprecedented way to study the viscosity and physics of plasma under the most extreme conditions imaginable. The implications of studying this heartbeat extend far beyond understanding a single black hole. This regular signal acts like a natural probe, allowing scientists to map the very geometry of space-time around the black hole. By analyzing the timing and energy of the pulses, researchers can test the predictions of Einstein's theory of general relativity with incredible precision in a regime where gravity is at its most powerful. It provides a unique laboratory for exploring how matter behaves at the limits of density and temperature, conditions that cannot be replicated in any particle collider on Earth. This rhythmic echo from the edge of oblivion is more than just a curiosity. It is a fundamental diagnostic tool, a direct sonar ping from the precipice of a black hole that is teaching us about the universal laws that govern all of creation, even in the darkest of places. While the rhythmic heartbeat of a black hole reveals the intimate dynamics around a single cosmic monster, our next discovery pulls the camera back to reveal the grandest and most mysterious force shaping the entire cosmos. This is the monumental effort of the Dark Energy Camera Legacy Survey, an ambitious project that isn't just mapping the sky, but is attempting to take the measure of nothing less than the fate of the universe itself. For over a decade, this powerful 570-megapixel camera, mounted on a telescope in Chile, has been engaged in a painstaking cosmic census, meticulously charting the positions and distances of hundreds of millions of galaxies across 1/8 of the entire night sky. Its primary target is the most profound mystery in modern cosmology: dark energy, the unknown force causing the expansion of the universe to accelerate. And its latest results are not just confirming its existence, they are presenting us with a puzzle so deep it threatens to unravel our fundamental understanding of physics. The survey's method is a masterpiece of indirect detection, relying on multiple techniques to triangulate the properties of dark energy. One key method involves using a specific type of supernova, a thermonuclear explosion of a white dwarf star, as a standard candle. Because we know their intrinsic brightness, measuring how dim they appear tells us their distance. By comparing this distance to the redshift of their host galaxies, a measure of how much the universe has stretched since the light left the star, scientists can chart the expansion history of the cosmos. Another technique maps the large-scale structure of the universe by measuring the subtle clustering of millions of galaxies. This cosmic web, the greatest structure in existence, holds an imprint of sound waves that race through the primordial plasma of the Big Bang. By measuring the apparent size of these frozen ripples at different epochs, astronomers can measure how the expansion rate has changed over billions of years. A third method, weak gravitational lensing, analyzes the tiny distortions in the shapes of distant galaxies caused by the warping of space-time from all the matter, both light and dark, between them and us. This creates a map of the cosmic mass and how it has clumped together over time. The combined data from all these methods delivers a powerful and consistent verdict. Dark energy is real, and it behaves like a cosmological constant, a force with a fixed strength that is woven into the very fabric of empty space itself. This is the simplest explanation within Einstein's theory of general relativity. But here is where the puzzle deepens to a truly confounding level. When cosmists try to calculate the theoretical value of this constant based on quantum physics, the number they get is absurdly, catastrophically large, about 120 orders of magnitude too big. A universe with that much dark energy would have been torn apart before any stars or galaxies could ever form. The fact that we exist means the value must be incredibly fine-tuned to an almost miraculous degree, but we have no physical principle to explain why. This is known as the cosmological constant problem, and it is arguably the worst theoretical prediction in the history of science. The latest results from the Dark Energy Survey have now sharpened this puzzle to a fine point. The data provides the most precise measurements ever of both the current expansion rate of the universe and the clumpiness of its large-scale structure. While the results largely confirm the standard model of cosmology, they also reveal a subtle but persistent tension. The universe today appears to be ever so slightly smoother, less lumpy in its distribution of galaxies and dark matter than our best models predict it should be, given the observed amount of dark energy. It's as if dark energy's repulsive force might be a tiny bit stronger than we thought, acting more efficiently to push matter apart and suppress the formation of the largest cosmic structures over the last few billion years. This tiny discrepancy is the kind of detail that keeps cosmologists awake at night. It could be a mere statistical fluke that will vanish with more data. Or it could be the first faint signal that dark energy is not a simple cosmological constant after all, but something dynamic and evolving, a force that changes over time. Perhaps it is a new kind of energy field, dubbed quintessence, that varies throughout space. Maybe it is a sign that Einstein's theory of gravity, while spectacularly successful, requires modification on the very largest scales. Each of these possibilities would represent a revolutionary upheaval in physics. The Dark Energy Camera Legacy Survey has done its job brilliantly, not by giving us all the answers, but by providing the sharpest data yet to ask the next, even deeper generation of questions. It has moved the mystery of dark energy from a theoretical concept to a precise observational problem, measuring the acceleration of the universe not as an idea, but as a reality, and in doing so, it has handed us the keys to the next great revolution in our understanding of reality itself. But our galaxy isn't just a place of orderly orbits, it's also a cosmic slingshot, a place of exile where stars are born only to be cast out into the endless dark. Our 15th oddity brings us to the phenomenon of hypervelocity stars, lone suns hurtling through the void at such incomprehensible speeds that they are achieving the ultimate escape velocity, breaking free from the Milky Way's gravitational grasp entirely. These aren't just fast-moving stars, they are celestial cannonballs, stellar projectiles racing toward a future of eternal solitude in the intergalactic wilderness. The first of these renegade stars was discovered in 2005, and its velocity was nothing short of breathtaking. It was measured to be moving at over 2.5 million miles per hour, more than 3 times the speed of our own sun's journey around the galactic center. At that rate, it's not just leaving the neighborhood, it's on a one-way trip out of the city, the state, and the country, destined to cross the immense, empty gulf between galaxies. Since that initial discovery, dozens more of these hypervelocity stars have been identified, each one a puzzle piece in a story of gravitational violence. The most widely accepted explanation for their origin points a finger directly at the heart of our galaxy, the supermassive black hole known as Sagittarius, a star. The theory, known as the Hill's mechanism, describes a gravitational dance of extraordinary precision and danger. Imagine a binary star system, 2 stars orbiting one another, that has the profound misfortune of wandering too close to the black hole's immense gravitational field. The black hole's tidal forces can violently disrupt this partnership. In a gravitational slingshot maneuver of unimaginable power, one star can be captured into a tight orbit around the black hole, while its companion is flung away at a significant fraction of the speed of light. The captured star becomes a prisoner of the abyss, while the other is sentenced to exile, ejected with enough kinetic energy to escape the galaxy forever. It's a cosmic trade-off, a transaction where the price of one star's freedom is the eternal imprisonment of its partner. However, not every hypervelocity star points back to the galactic center. Another compelling factor for these stellar speedsters is the aftermath of a supernova explosion within a tight binary star system. In this scenario, 2 stars are locked in a mutual orbit. When the more massive one exhausts its fuel and explodes in a supernova, it can suddenly lose a significant portion of its mass. If the explosion is asymmetrical, if it gives the dying star a kick in one direction, it can disrupt the gravitational balance of the system entirely. The remaining companion star, suddenly freed from the bond of its obliterated partner, can be flung off on a new, high-speed trajectory, like a ball released from a swung sling. Alternatively, if the supernova remnant collapses into a dense neutron star or black hole, and the explosion is perfectly symmetric, the sudden loss of mass can simply unbind the system, ejecting the companion with its original orbital velocity. The study of these runaway stars offers us a unique form of cosmic archaeology. By tracing their paths backwards across the sky, astronomers can sometimes pinpoint their precise origin point, effectively using them as probes to map the gravitational landscape of the galaxy. A hypervelocity star fleeing the galactic center confirms the violent dynamics at play around our central black hole. One originating from a known supernova remnant provides a living testament to that ancient cataclysm. They carry the story of their birth and their violent ejection encoded in their speed and trajectory. Furthermore, by analyzing their composition through spectroscopy, scientists can often determine what type of environment they came from, whether it was the metal-rich core of the galaxy or a more distant, sparser region. These stars are more than just curiosities. They are messengers telling us stories about the most extreme and energetic events that can happen in a galaxy, events that are otherwise difficult to observe directly. They remind us that the cosmos is a dynamic and often violent place, where a star's journey can be forever altered in a single, catastrophic moment. While our galaxy ejects stars on one-way journeys into the void, our own solar system appears to be hiding a giant secret of its own, a ghost of gravity that whispers from the darkness beyond Neptune. This is the compelling and controversial hypothesis of Planet 9, a proposed world of such size and distance that it would fundamentally rewrite the map of our cosmic backyard. The evidence for this unseen planet doesn't come from a direct glimpse, but from the peculiar ballet of much smaller, icy bodies in the far outer solar system, a region we've only begun to explore. These remote objects, known as extreme trans-Neptunian objects, follow elongated orbits that take them hundreds of times farther from the Sun than Earth. The curious thing isn't their distance, but their alignment. The most distant of these objects, like the dwarf planet Sedna, have orbits that are curiously clustered together. Their points of closest approach to the Sun, their perihelia, are grouped in the same region of space, and their orbits are tilted in a similar direction. According to the laws of probability, this specific clustering should be incredibly rare, a statistical fluke that would only happen by random chance about 0.007% of the time. It's as if you scattered a handful of marbles on a vast floor and found they had all, against all odds, rolled to rest pointing in the same exact direction. This bizarre orbital syncopation strongly suggests they are not moving independently. Something massive must be herding them, its gravity acting as an invisible shepherd guiding their path. That shepherd, according to the calculations of astronomers Konstantin Batygin and Mike Brown, is a planet, not just any planet, but a super-Earth or a mini-Neptune with a mass estimated to be 5 to 10 times that of our own world. Its orbit would be equally colossal, taking between 10 and 20,000 years to complete a single, lazy journey around the Sun, never venturing closer than about 200 times the Earth-Sun distance and swinging out as far as 1,200 times that distance into the profound blackness. At such a distance, it would reflect so little sunlight that it has eluded every major sky survey to date, a dark giant hiding in plain sight, its presence betrayed only by the subtle gravitational tugs it exerts on its smaller, icy neighbors. The ongoing search for this hidden world is a monumental effort that combines cutting-edge telescope technology with painstaking data analysis. Projects like the Subaru telescope's hypersensitive hyper-subprime cam on Mauna Kea are systematically scanning the vast swath of sky where the planet's predicted orbit might lie, looking for a single, faint, slowly moving dot among billions of stars. The challenge is immense. It's like searching for a single specific glacier in the Arctic night using only a flickering candle. The planet moves so slowly against the backdrop of the stars that detecting its motion requires comparing images taken weeks or months apart, a digital game of spot the difference on a cosmic scale. Yet the failure to find it thus far has opened the door to even more exotic possibilities. If a planet of that size and distance is so difficult to see, perhaps it isn't a planet at all. One of the most fascinating alternative theories proposes that the gravitational anomalies could be caused by a primordial black hole. This wouldn't be the gigantic black hole at the center of a galaxy, but a tiny, ancient relic from the very first moment of the Big Bang. A black hole with the mass of 5 Earths would be only about the size of a bowling ball, yet its gravitational pull would be identical to that of a planet. It would be utterly black, detectable only through its gravity or through the rare, faint flash of light if it devoured a passing chunk of ice and rock. The idea is highly speculative, but it highlights the depth of the mystery. We are dealing with a gravitational signature that demands a massive object, and our inability to see that object forces us to consider every conceivable option, no matter how strange. Whether the culprit is a frozen giant or a captured black hole, the implications of its discovery would be revolutionary. Confirming Planet 9 would not just be about adding a new planet to our textbooks, it would be a stunning revelation about the formation and evolution of our solar system. How did such a large planet get so far out? Was it ejected from the inner solar system in its chaotic youth? Or was it an interstellar rogue captured by the sun's gravity long ago? Its existence would suggest that our solar system story is far more dynamic and violent than we ever knew, with a chapter still waiting to be read in the light of a distant, undiscovered sun. This gravitational ghost, whether world or singularity, represents the ultimate frontier of exploration in our own celestial neighborhood. A reminder that even here at home, the cosmos is still capable of holding breathtaking secrets. Moving from the slow, gravitational whispers of a potential hidden planet, we now confront a cosmic phenomenon that is the exact opposite, a scream of energy so intense and so brief that it defies belief. This is the enigma of fast radio bursts, or FRB, and our 17th oddity focuses on the one that changed everything. The first known repeater. Imagine a flash of radio waves so powerful that in a single millisecond, it can release more energy than our sun puts out over several decades. Now imagine that same flash not as a one-off event, but repeating again and again, seemingly at random from a single point in the sky. This is FRB 1200 and 1102. A celestial beacon of pure mystery that transformed FRBs from a curiosity into one of the most profound puzzles in modern astronomy. The story of FRBs began with a bit of cosmic forensics. The first one was discovered in 2007 by astronomers sifting through old archival data from the Parkes Radio Telescope in Australia. It was a blindingly bright spike in the data that lasted just 5 milliseconds. For years, these events were written off as potential terrestrial interference glitches from microwave ovens on site or other human-made sources. But as more were found by other telescopes around the world, their extraterrestrial origin became undeniable. The key clue was something called dispersion. As these radio waves travel across millions of light-years of intergalactic space, they pass through a sparse sea of free electrons. Higher frequency waves travel slightly faster than lower frequency ones, so a burst that starts out as a compact signal gets stretched out, arriving at our telescopes as a descending chirp. By measuring how much the burst is stretched, astronomers can calculate the vast distance it has traveled. These were not local events, they were coming from other galaxies. Then, in 2016, everything changed. FRB 1200 and 1102 did something no other FRB had done before. It repeated. This wasn't a predictable repetition, but a sporadic series of outbursts, sometimes with multiple bursts in a single day, and then going silent for months. This single fact immediately ruled out cataclysmic one-time events as the source for at least some FRBs. You can't have a star explode in a supernova over and over again. The repeater had to be powered by something that could survive the event, an engine that could fire multiple times. The race was on to pinpoint its location, and when astronomers succeeded, the answer was just as astonishing as the burst itself. FRB 1200 and 1102 was localized to a tiny, incredibly faint dwarf galaxy over 3 billion light-years away. Even more intriguingly, It was positioned right in the midst of a bright, persistent radio source, which itself was embedded in a nebula of glowing gas. This environment was a crucial clue pointing toward an extreme and violent birthplace. The breakthrough in understanding came from a fortunate event within our own galactic neighborhood. In April 2020, a magnetar in our own Milky Way galaxy, one of those magnetic monsters we discussed earlier, erupted not only with its usual X-rays, but with a blast of radio waves that looked for all the world like a weak FRB. This was the smoking gun. It strongly suggested that at least some FRBs are indeed generated by magnetars. The theory is that the unimaginable stresses in a magnetar's crust can cause stellar quakes, sudden fractures that release torrents of energy, accelerating particles and creating powerful shocks that then emit these brilliant, coherent beams of radio waves. It's the cosmic equivalent of the crack of a whip, but on a scale that dwarfs all human comprehension. Yet for all this progress, the mystery is far from completely solved. While the galactic magnetar connection explains one-off FRBs and perhaps some repeaters, the behavior of FRB 1200 and 1102 and others like it remains deeply puzzling. Their repetitions are often clustered and seemingly random, and some show patterns that are difficult to explain with simple star quakes. Furthermore, the energy required for the most extreme bursts detected in distant galaxies pushes the magnetar model to its absolute limits, requiring efficiencies that border on the impossible. This enduring enigma is what keeps the door open for more speculative and thrilling ideas. One of the most captivating alternative theories returns to a concept we encountered with Tabby's star, alien technology. The idea, proposed by theorists like Avi Loeb, is that these bursts could be evidence of interstellar light sails. A civilization advanced enough to want to propel spacecraft across the vast distances between stars could use a powerful beam of energy to push a light sail to relativistic speeds. From our distant perspective, as that beam sweeps across the sky, it would appear as an incredibly bright, ultra-fast flash of radio waves. The repeating nature could be explained by the beam periodically tracking onto our line of sight as the transmitter moves. While this is considered a less likely explanation by most astrophysicists, who adhere to the principle of seeking natural causes first, its continued discussion highlights the sheer profundity of the puzzle. These bursts sit at the very edge of what we know is physically possible, a boundary where conventional physics begins to blur with the stuff of science fiction. Whether the final answer is shaking neutron stars or something even more incredible, fast radio bursts remind us that the universe is still shouting its secrets, and we are only just beginning to learn how to listen. While the idea of a rogue black hole or a hidden planet within our own solar system speaks to mysteries on a local scale, our 18th oddity presents a gravitational puzzle of truly epic proportions, a force so immense it is herding entire galaxies like cosmic sheep. This is the enigma of the Great Attractor, a gravitational anomaly of such staggering power that it is pulling our entire Milky Way galaxy, along with our entire local group of galaxies and thousands of others, on a relentless journey through the universe at a breathtaking speed of over 1.5 million miles per hour. We are not drifting aimlessly, we are on a collision course with a something we cannot see, a destination hidden behind a veil of our own galaxy's making. The story of this discovery begins not with seeing this attractor, but with mapping the consequences of its pull. For decades, astronomers have been measuring the precise velocities of galaxies relative to the overall expansion of the universe, a field known as peculiar velocity. When they mapped our local cosmic neighborhood, a startling pattern emerged. Instead of all galaxies moving apart smoothly with the Hubble flow of expansion, a vast swath of them, including us, were all streaming in the same direction, toward a single point in the sky deep within the constellation Centaurus. This collective motion, dubbed the dark flow, pointed unequivocally to the existence of a concentration of mass of almost unimaginable density, a gravitational anchor around which our entire region of space seems to be revolving. The profound frustration in solving this mystery is that the exact spot toward which we are all being pulled lies directly behind the crowded, dusty central plane of our own Milky Way galaxy. This region is known as the zone of avoidance because the dense clouds of gas and dust effectively obscure our optical view of the universe beyond, like trying to see a distant mountain range through a thick, perpetual fog. For years, the Great Attractor remained a ghost, its nature undefined, known only by its irresistible gravitational influence. The key to peering through this galactic curtain has been technology that can see in wavelengths of light that dust cannot block. Radio, infrared, and most importantly, X-ray telescopes have slowly pulled back the veil, revealing that the Great Attractor is not a single, incomprehensibly massive object. Rather, it is the heart of a colossal supercluster of galaxies, a galactic metropolis known as the Laniakea supercluster, a Hawaiian word meaning immense heaven. Our Milky Way is merely a suburban outlier on the far-flung edge of this vast structure. At the core of Laniakea lies the Norma cluster, an immensely dense knot of galaxies, and beyond that, an even more massive concentration of mass known as the Shapley supercluster. It appears that the gravitational pull we experience is the combined effect of all this mass: the Norma cluster, the Shapley supercluster, and other massive structures in this direction acting together. However, the puzzle is not completely solved. Even when accounting for all the visible mass in these superclusters, there seems to be a discrepancy. The strength of the pull still suggests there might be more mass present than we can currently account for with our surveys. This leads to the tantalizing possibility that there are still entire walls of galaxies, vast filaments of the cosmic web, hidden behind the zone of avoidance that we have yet to fully map. The Great Attractor may ultimately be the sum of many attractors, a complex tapestry of dark matter halos and galaxy clusters whose full scope we are only beginning to appreciate. It stands as a humbling reminder that some of the universe's largest structures can remain hidden in plain sight, their presence felt long before they are ever seen, guiding the motion of galaxies on a journey whose ultimate destination we are still working to reveal. If the gravitational pull of the Great Attractor represents an overwhelming concentration of cosmic mass, then our 19th oddity presents the exact opposite, a staggering, almost inconceivable absence. Welcome to the Boötes Void, a spherical region of space so profoundly empty it has earned the ominous nickname, the Great Nothing. Stretching an astonishing 330 million light-years across, this void is not just a gap between galaxies. It is a cavernous bubble within the cosmic web, a place where the universe's usual bustling density of galaxy clusters and superclusters gives way to a haunting, almost total emptiness. To grasp its scale, consider that our entire local group of galaxies, including the Milky Way and Andromeda, could travel through this void for hundreds of millions of years without coming anywhere near another major galaxy. It is a desert on a scale that defies human comprehension, and its existence presents a monumental challenge to our understanding of how the universe organized itself after the Big Bang. The void's discovery in the 1980s was a moment of profound shock for astronomers mapping the large-scale structure of the cosmos. According to the prevailing cosmological models, the universe should have a somewhat bubbly structure, with filaments and walls of galaxies surrounding smaller voids. But the Boötes Void was something else entirely. Its sheer size was the problem. It was far larger than any theoretical model predicted could form through the standard process of gravitational collapse and cosmic expansion. It was as if we found a single, perfectly spherical room 1,000 miles wide inside a vast apartment building, a space that the blueprints insist should not and could not exist. This great nothingness became an existential threat to the standard model of cosmology, a glaring anomaly that demanded an explanation. Initial surveys suggested the void was almost completely barren, with early estimates finding only a handful of galaxies within its immense volume. If the average density of the universe were applied to a space that size, it should contain roughly 10,000 galaxies. Instead, only about 60 have been confirmed. This extreme underdensity means the void is not just a low-density region. It is a place where the very rules of structure formation seem to have been suspended. The question of how such a vast emptiness came to be has fueled decades of scientific debate and some truly spectacular theories. One compelling line of thought suggests that the Boötes void might not be a single void at all, but the phenomenal and unlikely merging of several smaller voids. As the universe expanded, smaller bubbles in the cosmic foam could have grown and eventually intersected, their boundaries dissolving to create one colossal empty region. This is a bit like several small soap bubbles on the surface of water coalescing into one giant bubble. While this is plausible, the probability of such a perfect merger happening on this scale is incredibly low, making the Boötes void a statistical outlier of cosmic proportions. A more radical and intriguing hypothesis proposes that the void is not empty, but is in fact filled with something we cannot easily see: dark matter. While dark matter is the gravitational glue that holds galaxies and clusters together, it is possible that a vast region could exist where the dark matter is distributed in an unusually smooth and uniform halo, failing to clump sufficiently to pull in the ordinary matter needed to form galaxies. In this scenario, the void is not a true absence of mass, but a failure of structure, a place where the dark matter skeleton never developed the joints and knots necessary to build the bright cities of stars we see elsewhere. We would be looking at a ghost of gravitational potential, a shadow universe where the blueprint for creation was drawn but never executed. The most mind-bending possibility, however, involves the very nature of reality itself. Some cosmologists have playfully suggested the void could be the imprint of an advanced Type 3 civilization on the Kardashev scale, a civilization that has harnessed the energy of entire galaxies. The idea goes that such a culture might eventually engage in the ultimate form of cosmic engineering, dismantling galaxies to fuel its expansion and leaving behind a sterilized, empty region. While this is a fascinating thought experiment, it is considered highly speculative and is not a mainstream scientific explanation. It does, however, highlight the sheer extremity of the phenomenon we are observing. The true key to understanding the Boötes void likely lies in the galaxies that do, against all odds, call it home. These isolated island universes are fascinating objects in their own right. Studies have shown that the few galaxies found within the void are often irregular and chemically primitive, with fewer heavy elements than galaxies in denser environments. This suggests they have led sheltered yet impoverished lives, isolated from the chaotic mergers and gas inflows that enrich galaxies in clusters. They have evolved slowly and quietly, like hermits in a vast desert, offering us a unique laboratory to study galaxy evolution in the most extreme isolation imaginable. Their very existence, sparse as it is, provides the crucial clues needed to map the void's true gravitational field and mass distribution, helping us distinguish between a true nothingness and a hidden fullness. The enduring mystery of the Boötes void serves as a crucial reminder of the limits of our knowledge. It is a blank spot on our map, a challenge to our models, and a catalyst for our imagination. Whether it is a statistical fluke, a domain of dark matter, or something even stranger, its existence forces us to refine our theories of cosmic evolution and acknowledge that the universe, in its immense complexity, is still capable of producing structures that leave us in awe of the great nothing. Now we arrive at a phenomenon so precisely beautiful and scientifically valuable that it seems almost too perfect to be natural, a celestial alignment that acts as a built-in telescope, gifted to us by the universe itself. This is the Einstein cross, a stunning example of gravitational lensing that transforms a single point of light into a cosmic work of art and a powerful tool for discovery. The concept was one of Einstein's most brilliant predictions, that a massive object like a galaxy would warp the fabric of space-time around it, bending the path of any light that passes nearby. This turns the galaxy into a gravitational lens capable of magnifying, distorting, and even multiplying the image of a more distant object lying directly behind it. The Einstein cross is the most elegant manifestation of this effect, where a single, distant quasar is lensed by a foreground galaxy, not into a smeared arc, but into four distinct, brilliantly sharp images arranged in a perfect cross pattern around the central lensing galaxy. The creation of this cosmic mirage requires a perfect and precise alignment. In the case of the original Einstein cross, a quasar located about 8 billion light-years away, a brilliantly luminous galactic core powered by a supermassive black hole, sits directly behind a galaxy that is closer to us, about 400 million light-years away. The gravitational field of this intervening galaxy is so intense that it splits the quasar's light into multiple paths as it travels toward Earth. Each path has a slightly different length, so the light in each image has been traveling for a slightly different amount of time. This means we are not just seeing four copies, we are seeing the same quasar at four slightly different moments in its history, an effect that allows for unprecedented study of its variability. But the true power of the Einstein cross and other similar systems lies far beyond their beautiful symmetry. They have become one of astronomy's most precise tools for tackling two of cosmology's biggest questions: the nature of dark matter and the expansion rate of the universe. By meticulously measuring the precise positions and brightnesses of the four quasar images, astronomers can reverse engineer the process. They can map the gravitational field of the lensing galaxy with incredible detail, revealing not just the distribution of the visible stars, but the invisible halo of dark matter that surrounds it. Any discrepancy between the predicted and observed lensing effect points directly to the properties of this dark matter, how it is clustered, how much of it there is, and whether it interacts with itself in ways we haven't predicted. It's a direct probe into the universe's hidden skeleton. Furthermore, because the light in each path takes a different amount of time to reach us, a flicker in the quasar's brightness will appear in each of the four images at a slightly different time. By carefully measuring these time delays, which can be days or weeks apart, astronomers can perform a remarkable feat of cosmic trigonometry. They can calculate the absolute distance to both the lensing galaxy and the background quasar with tremendous accuracy. This provides an independent measurement of the Hubble constant, the rate of the universe's expansion. In an era where different methods for measuring this rate are yielding conflicting results, a tension that might point to new physics, the Einstein cross and other lensed quasars offer a completely different, gravity-based way to resolve the dispute. These impossible crosses in the sky are far more than just pretty pictures. They are natural laboratories, cosmic instruments that allow us to weigh the invisible and measure the expansion of everything, all from a single, fleeting, and perfect alignment. While our journey has taken us to the edges of the cosmos and back in time, our 21st oddity brings us to a cosmic anachronism, a galactic relic that has somehow defied the fundamental rule of the universe, that to grow is to change. Meet NGC 1277, a galaxy that astronomers have dubbed a cannibal, but not for the reason you might think. This label doesn't refer to a monstrous devourer of other galaxies, quite the opposite. It's a cosmic hermit, a fossilized island that has stubbornly refused to interact with the outside world for nearly the last 10 billion years. While our own Milky Way and its neighbors have been constantly merging, colliding, and cannibalizing smaller galaxies in a chaotic dance of growth and evolution, NGC 1277 has remained in a state of suspended animation, offering us a pristine, untouched window into what the very first giant galaxies looked like in the infant universe. This ancient galaxy, located 220 million light-years away in the constellation Perseus, is a lenticular galaxy, a fuzzy disk shape that sits somewhere between a spiral and an elliptical. Its most striking feature is its population of stars. Unlike most large galaxies we observe, which are a vibrant mix of old red stars and young blue stars constantly being born from fresh gas, the stars in NGC 1277 are all ancient and red. There is no evidence of recent star formation, no glowing pink clouds of hydrogen gas where new suns are being born. Its star-making machinery shut down eons ago, and without any galactic collisions to stir things up and inject new fuel, it has remained frozen in time, a cosmic museum piece. It's like finding a lost city where the inhabitants simply stopped building 10,000 years ago, and everything has been perfectly preserved exactly as they left it. The galaxy's isolation is its defining characteristic. It orbits on the outskirts of the massive Perseus cluster, a bustling metropolis of thousands of galaxies. But while its neighbors have been interacting and merging, NGC 1277 has been flying through the relative emptiness of the cluster's outskirts at a tremendously high velocity, moving far too fast to get caught up in the gravitational tug of war that shapes other galaxies. This high-speed trajectory has allowed it to sail through the last 10 billion years completely unscathed, a lone voyager that has witnessed the entire history of galactic evolution unfold around it without ever participating. But the most stunning secret this fossil galaxy holds is buried deep in its silent core, a supermassive black hole of such impossible proportions that its very existence challenges our understanding of how these cosmic engines form. Typically, the mass of a galaxy's central black hole correlates with the mass of its central bulge of stars. The larger the bulge, the larger the black hole. In the Milky Way, our central black hole, Sagittarius A, makes up a tiny fraction of a percent of the bulge's mass. The black hole at the heart of NGC 1277 is an utter monstrosity by comparison. Despite the galaxy itself being only a quarter the size of the Milky Way, its black hole weighs in at a staggering 17 billion solar masses, making it one of the most massive black holes ever discovered. This behemoth constitutes a whopping 14% of the entire galaxy's central bulge mass, a ratio so wildly out of proportion with every known rule that it seems to break physics. This impossible ratio is the strongest clue that we are looking at a primordial relic. The prevailing theory for how supermassive black holes grow is that they start from smaller seeds and then steadily accumulate mass over billions of years through mergers and by feeding on gas. But the sheer size of this black hole in such an undeveloped galaxy suggests a different origin story altogether. It points to a scenario where the black hole formed incredibly early and incredibly massive right from the beginning, perhaps from the direct collapse of a gigantic cloud of primordial gas in the universe's first few 100 million years. In this model, the black hole didn't grow the galaxy grew around the black hole. The presence of this leviathan, frozen in time, suggests that the earliest galaxies in the universe were not built from the ground up by stars, but were instead seeded from the top down by these incomprehensibly large black holes that dictated their growth from the very start. Studying NGC 1277 is like finding a living dinosaur. Its pristine state allows astronomers to test fundamental ideas about galaxy formation without the complicating factors of later mergers and interactions. It provides a critical data point suggesting that the earliest giant galaxies were not the grand spirals we see today, but were instead these compact, red and dead spheroids dominated from birth by black holes of unimaginable size. This cosmic fossil forces us to rewrite the early chapters of the galactic story, revealing a universe where the rules were different and where the ghosts of those first titans still wander among us silent and unchanged. Imagine scanning the skies with one of the most powerful radio telescopes ever built, expecting to map the familiar terrain of distant galaxies and stellar nurseries, only to stumble upon perfect, ghostly circles so vast they could easily swallow entire galaxies whole. This is exactly what happened in 2019 when astronomers using the Australian Square Kilometre Array Pathfinder, or a SKAP, discovered the first of what we now call odd radio circles, or ORCS. These enigmatic structures appear exclusively in radio wavelengths, leaving no trace in optical, infrared, or X-ray light. They are cosmic fingerprints, immense rings of radio emission etched onto the sky with a clarity and scale that defies immediate explanation, and their discovery has sent astronomers scrambling for answers. The sheer size of these circles is the first thing that beggars belief. They are not small. They span hundreds of thousands of light years across, meaning each one is several times larger than our entire Milky Way galaxy. If one were close enough to be visible to the naked eye, it would appear larger than a full moon. Yet, despite their monumental proportions, they are incredibly faint, which is why they remained hidden until our radio telescopes achieved the sensitivity and survey speed of modern instruments like a SKAP. Their perfect circularity is another striking feature, suggesting a symmetrical, energetic event that propagated outward as a near-perfect sphere. The few that have been found all share this characteristic, and most intriguingly, many of them seem to have a galaxy at their very center, like a bullseye hinting at the source of the explosion. So what could possibly create such enormous, ring-shaped signals? The most widely accepted theory points to a truly galactic-scale cataclysm, the shockwave from a starburst event. In the heart of some galaxies, a ferocious burst of star formation can occur, creating thousands of massive stars in a relatively short period. These stars live fast and die young, exploding as supernova in quick succession. The combined energy of these explosions can drive a powerful galactic wind, a bipolar outflow of material that blasts out from the galaxy's poles. If we are looking directly down the barrel of this outflow, the shock wave at its leading edge would appear as a nearly perfect sphere expanding into the intergalactic medium. This shockwave accelerates electrons to near light speed, causing them to spiral around magnetic fields and emit synchrotron radiation, which we detect as radio waves. This theory neatly explains the central galaxy and the circular shape, painting a picture of a galaxy undergoing a violent, transformative burst of energy that reverberates across intergalactic space. However, not all ORCS have a clearly identifiable central galaxy, which has led to other, even more exotic possibilities. One fascinating idea is that we might be seeing the aftermath of a merger between two supermassive black holes. When two black holes finally spiral together and coalesce, they release a titanic burst of gravitational waves. It's theorized that this sudden, asymmetrical loss of mass could generate a powerful jet of energy shooting out from the newly merged black hole. The interaction of this jet with the surrounding gas could create an expanding spherical shockwave that would manifest as one of these mysterious radio circles. This would be a previously unknown signature of one of the universe's most energetic events, a kind of gravitational wave aftershock visible across the electromagnetic spectrum. Yet, the most mind-bending hypothesis pushes the boundaries of known physics into the realm of science fiction. Could ORCS be the throats of traversable wormholes? According to some solutions in general relativity, a stable, traversable wormhole, a shortcut through space-time, would require exotic matter with negative energy density to keep its throat open. The theorized interaction of this exotic matter with the surrounding space-time could potentially produce a distinct spherical signature detectable in radio waves. From our perspective, looking down the tunnel of a wormhole, we might see the inner walls of the throat as a bright, ring-like structure. While this is undoubtedly the most speculative explanation, the fact that it is even discussed in serious scientific papers underscores just how perplexing and unprecedented these objects truly are. They defy simple classification, forcing us to consider all possibilities, no matter how extraordinary. The mystery of the odd radio circles is a beautiful example of how every time we build a new window to view the universe, we are guaranteed to see something completely unexpected. They are not merely new objects to add to a catalogue. They are profound puzzles that challenge our understanding of galactic evolution, energy transfer on massive scales, and perhaps even the fundamental nature of space-time itself. As more of these ghostly circles are discovered and studied with even more powerful telescopes, they promise to either neatly fit into our existing models of astrophysical shocks or force us to invent an entirely new chapter in physics to explain their impossible presence. Imagine a world where the very ground beneath your feet is more precious than any treasure ever dreamed of on Earth. This is the reality of Planet 55 Cancri, a super-Earth whose likely composition has earned it the sensational nickname of the Diamond Planet. Located a mere 40 light-years away in the constellation Cancer, this world is a blistering testament to planetary extremes, orbiting so close to its sun-like star that a single year, one full orbit takes less than 18 hours. The proximity creates an environment of almost incomprehensible violence and heat, with surface temperatures soaring to over 2,400 degrees Celsius, hot enough to melt iron and vaporize rock. It is a realm where the very concept of a solid surface is redefined, not as stone or soil, but as a global, roiling ocean of incandescent lava. The hypothesis that this world could be rich in diamond stems from a careful analysis of its parent star, 55 Cancri A. Spectroscopy reveals that this star possesses an unusually high carbon-to-oxygen ratio. In the protoplanetary disk from which planets form, the building blocks available are dictated by the star's composition. A high abundance of carbon over oxygen suggests that the planets that coalesced around this star would be fundamentally different from our own silicate-rich Earth. Instead of a world built from oxygen-rich minerals like quartz and feldspar, you would form a planet dominated by carbon compounds. Under the immense pressures and searing temperatures within a large, rocky planet like 55 Cancri, that carbon is forced into the most stable structure possible, the crystalline lattice of diamond. This doesn't mean the planet is a single, flawless gemstone sparkling in the void. The reality is far more strange and geologically active. Scientists believe its interior could be a vast mantle of solid diamond, dozens of miles thick, but its surface is a global inferno. The incredible heat from its star, combined with intense tidal forces that likely keep the planet tidally locked with one permanent day side and one permanent night side, ensures that its crust is a perpetual, churning ocean of molten lava. Some models even suggest that the planet could experience silicon-based volcanism, where the lava is composed not of molten rock as we know it, but of superheated silicon carbide, a compound that would itself break down under the extreme heat to release more carbon into the mix, further feeding the diamond-forming engine deep below. The existence of such a world fundamentally challenges our classification of planets and our understanding of their potential diversity. We are accustomed to rocky worlds, gas giants, and ice giants, but a carbon planet represents an entirely new category. It suggests that the universe can forge worlds from a much broader periodic table of elements than we once imagined. If our solar system had formed around a carbon-rich star, Earth itself might have been a diamond planet, a stunning thought that reshapes our perspective on our own place in the cosmos. 55 Cancri is not a celestial jewel box but a laboratory of extreme planetary science, a place where the common element of carbon is transformed under immense pressure into a testament of nature's boundless creativity. Now we encounter a cosmic horror story written in gravity and radiation, a binary system that has earned the chilling nickname of the Black Widow pulsar. Picture a stellar pairing with a gruesomely one-sided relationship, where one member is systematically destroying the other, not with claws or teeth, but with a relentless blast of energy so intense it is quite literally boiling its partner away into nothingness. This is the ultimate parasitic relationship, playing out over millions of years and offering a terrifyingly elegant solution to a long-standing astronomical mystery. How do you create the fastest spinning objects in the universe? At the heart of this system lies a pulsar, the ultra-dense, city-sized remnant of a supernova explosion. This particular pulsar is a special class known as a millisecond pulsar, spinning hundreds of times per second and emitting a lighthouse-like beam of radiation that sweeps across the sky with metronomic precision. But this incredible rotational speed is the first clue to its violent nature. A pulsar shouldn't be able to spin that fast on its own. It's like a top that keeps spinning long after it should have slowed down. The only way it could have gained such dizzying momentum is by stealing it, and that's where its unfortunate companion comes in. The victim in this tale is a small, low-mass star, perhaps similar to our Sun or even smaller. The two objects are locked in a desperately close orbital dance, completing a full revolution around each other in just a matter of hours. This proximity is the key to the doom of the smaller star. The pulsar's powerful gravitational field and its intense radiation, a searing torrent of high-energy particles and gamma rays, are bombarding the companion star's surface, heating it to temperatures of over 10,000 degrees Celsius and forcefully stripping its outer layers away. This process, known as ablation, is like holding a stellar blowtorch to a ball of ice, causing it to vaporize continuously. The pulsar is actively consuming the very thing that keeps it alive. This stolen material doesn't just vanish. As it is ripped from the companion, it forms a vast cloud of superheated plasma that envelops the entire binary system. This cloud occasionally eclipses the pulsar's signal from our view on Earth, creating the temporary radio silence that helped astronomers first identify these bizarre objects. But more importantly, some of this ablated material doesn't escape entirely. A portion of it is captured by the pulsar's immense gravity and funneled onto its magnetic poles. As this incoming gas spirals down, it transfers its angular momentum to the pulsar, causing it to spin faster and faster. This is the ultimate act of cosmic vampirism. The pulsar is draining the life and rotational energy from its partner to fuel its own frantic spin, all the while blasting it with the radiation that is causing the destruction in the first place. The fate of this system is as inevitable as it is grim. The companion star is losing a mass equivalent to that of our entire planet Jupiter every 100 million years. Given enough time, and astronomical time is one thing this system has in abundance, the process will complete. The smaller star will be entirely evaporated, leaving behind no trace but a faint, expanding cloud of ionized gas. All that will remain is the now isolated millisecond pulsar spinning silently and rapidly in the void, a grim monument to the companion it consumed. This final product is the answer astronomers had long sought. The Black Widow system is the missing link that explains the existence of isolated millisecond pulsars. They weren't born that way, they were spun up by a partner they later destroyed. These horrifying yet fascinating systems are more than just celestial curiosities, they are extreme natural laboratories. The intense radiation environment around the pulsar is unlike anything we can create on Earth, allowing us to study how matter behaves under the most ferocious conditions. Furthermore, by studying the rate of ablation, astronomers can learn about the composition and internal structure of the companion star in a way that would otherwise be impossible, as if the pulsar's deadly beam is performing a brutal but informative cosmic dissection. The Black Widow pulsar is a stark reminder that the universe operates on a scale of both sublime beauty and terrifying violence, where the creation of a spinning marvel is directly tied to the utter annihilation of another star. Now we arrive at one of modern cosmology's most persistent and confounding puzzles, a discrepancy so stubborn that it threatens to unravel our most fundamental understanding of the cosmos. This is the Hubble Tension, a growing conflict between two impeccable ways of measuring the universe's expansion rate, a disagreement that suggests either we are making a profound mistake or the universe is playing by a set of rules we have not yet discovered. The expansion rate is quantified by the Hubble constant, a number that represents how fast, in kilometers per second, A galaxy is receding from us for every megaparsec of distance it gains. Pinpointing this number is akin to finding the cornerstone of cosmology. It sets the age of the universe, dictates its future fate, and calibrates almost every measurement we make across deep space. The problem is, we now have two gold standard methods for calculating this number, and they are delivering answers that refuse to agree. The first method builds a distance ladder using the universe's most reliable mile markers. It starts in our local cosmic neighborhood with Cepheid variable stars, pulsating stars whose intrinsic brightness is directly tied to their pulse rate. By measuring their pulse, we know their true brightness, and by comparing that to how dim they appear, we can calculate their exact distance. This allows us to calibrate the next rung of the ladder, which includes even brighter standard candles like Type 1, a supernova stellar explosions so uniform in their peak brightness that they can be used to measure distances to galaxies far across the universe. By meticulously climbing this ladder, astronomers have arrived at an incredibly precise value for the Hubble constant. The latest results from the SH0ES team, using this cosmological distance ladder, have honed in on a specific expansion rate with a margin of error of less than 2%. The second method takes a completely different approach, looking back to the very beginning of everything. It uses the afterglow of the Big Bang itself, the cosmic microwave background, as a snapshot of the infant universe. By mapping the tiny temperature fluctuations in this ancient light with exquisite precision, as missions like the Planck satellite have done, cosmologists can calculate the ingredients of the early universe, the amounts of dark matter, dark energy, and ordinary matter. The standard model of cosmology, known as lambda cold dark matter, then tells us exactly how this primordial universe should have evolved and how fast it should be expanding today. This method is a top-down approach, working from the initial conditions forward, and it too delivers a result with stunning precision. Here is the rub: these two methods, both executed with flawless technical skill and peer-reviewed rigor, do not match. The local distance ladder measurement gives a significantly higher value for the expansion rate than the prediction from the primordial cosmic microwave background. The discrepancy is not a small, negligible margin of error. It is a persistent gap of several kilometers per second per megaparsec, a difference that has only grown more significant as our measurements have become more precise. It's as if two of the world's most accurate clocks, built by master watchmakers using different principles, began steadily ticking out of sync. This isn't just a minor calibration issue. It is a direct conflict that suggests a fundamental flaw in our understanding. This growing tension has forced cosmologists to consider truly revolutionary possibilities. Perhaps dark energy, the mysterious force accelerating the expansion, is not a constant after all, but an evolving force that has grown stronger over time, throwing off the predictions based on the early universe. Maybe dark matter possesses unknown properties, allowing it to interact with itself or with light in ways we haven't accounted for. There's even a speculative idea that the universe might contain a new type of relativistic particle, like a sterile neutrino, that was present in the early cosmos and altered its evolution in a way that the Planck data wouldn't show. The most extreme suggestion is that we might need to modify Einstein's theory of gravity itself on the largest scales, a daunting proposition given how successfully general relativity has passed every other test for a century. The Hubble tension is more than an academic disagreement. It is a beacon pointing toward the next frontier of physics. It tells us that our otherwise spectacularly successful standard model of cosmology is incomplete. Somewhere hidden in the details of this discrepancy lies a clue to a deeper layer of reality, a new piece of physics that will ultimately lead to a richer, more complete theory of the universe. This tension is not a failure of science, but a thrilling indication that we are on the verge of a profound discovery, a moment where the cosmos itself is challenging us to look deeper and think bigger. While we often imagine galaxies as glittering cities of stars, our next discovery reveals a ghost, a cosmic entity so ethereal it barely seems to exist at all. This is the see-through galaxy, an object officially designated as Dragonfly 44's even more enigmatic cousin, a patch of the universe where the rules of galactic construction appear to have been rewritten by an unseen hand. If finding a galaxy made of 99% dark matter was shocking, discovering one that is almost completely transparent is nothing short of revolutionary. These are not just dark matter dominated, they are ultra-diffuse galaxies, or UDGS, so sparse and star-poor that they boast a surface brightness hundreds of times fainter than our own night sky. They are the phantoms of the cosmos, vast structures of incredible size that contain almost none of the luminous matter we expect to find, floating through space like celestial jellyfish, visible only to our most powerful and patient telescopes. The revelation of these impossible objects came as a direct result of technological innovation. Traditional astronomical surveys are designed to find things that are bright, automatically filtering out faint, low-contrast smudges as noise or artifacts. It took a specially designed telescope, the Dragonfly Telephoto Array, to finally see them. This instrument, built from a network of commercially available telephoto lenses, is uniquely optimized to detect the faint, sprawling glow that other telescopes miss. By minimizing internal light scattering, it acts like a pair of astronomical glasses, bringing these blurry, extended ghosts into focus for the very first time. What it revealed was a population of galaxies that had been hiding in plain sight, not in the empty voids of space, but often right within massive galaxy clusters, the busiest and most crowded neighborhoods in the universe. This location is the first major clue to their nature and the source of their profound mystery. How can something so delicate and diffuse survive in an environment of such gravitational violence? Galaxy clusters are cosmic mosh pits where the immense tidal forces generated by hundreds of galaxies swinging past each other should easily tear a flimsy, low-density galaxy apart. The fact that these see-through galaxies not only exist but are quite common in these regions suggests they possess a hidden source of strength, a gravitational anchor that holds them together against all odds. That anchor, once again, is dark matter. Measurements of the stars within them, the few that there are, show they are moving at velocities that should instantly fling them out into the void. The only thing keeping them tethered is the immense, invisible mass of a dark matter halo, a gravitational scaffold of incredible density that provides the skeleton for a galaxy with almost no flesh. This presents a paradox that strikes at the heart of galaxy formation theory. In our standard model, a galaxy begins with a halo of dark matter whose gravity pulls in ordinary gas. This gas cools, condenses, and eventually forms stars. The ratio of dark matter to normal matter is generally consistent, but in these see-through galaxies, that process seems to have been catastrophically interrupted. They have the massive dark matter halo of a large galaxy, but for some reason, the star formation engine failed almost completely. One compelling theory points to their violent environment. Perhaps these galaxies were once more normal, but as they fell into the dense cluster, the vast clouds of hot gas that permeate the cluster interior acted like a cosmic blowtorch, violently stripping away their star-forming fuel through a process called ram pressure stripping. What remains is the dark matter backbone and a handful of stars that managed to form before the gas was ripped away, a galactic ghost that continues to orbit on the power of its invisible mass alone. An even more intriguing possibility is that these galaxies are failed giants from the early universe. Some cosmological simulations suggest that the largest dark matter halos in the infant cosmos were spinning extremely rapidly. This high spin would have spread the infalling gas thin, preventing it from reaching the densities necessary to trigger efficient star formation. In this scenario, the see-through galaxy was never meant to shine brightly. it was born a ghost, a vast and quiet realm of dark matter that never got the chance to build a stellar civilization. Their existence forces us to accept that dark matter does not always command visible matter to coalesce into light. Sometimes it simply holds a silent, empty fortress, a monument to the potential for a galaxy that never was. These impossible dark galaxies are not just oddities, they are a fundamental challenge, revealing a diversity in galactic evolution that we are only beginning to comprehend, and proving that the universe's construction plans are far more varied and mysterious than we ever dreamed. We often picture the auroras of Earth, the dancing northern and southern lights, as a privilege of planets with strong magnetic fields, a protective shield that funnels charged solar particles toward the poles to create a spectacular celestial display. So imagine the astonishment when astronomers discovered that Mars, a planet that lost its global magnetic shield billions of years ago, is hosting its own breathtaking light show. This isn't a faint glimmer, it's a vast, diffuse aurora that envelops the entire planet in a soft, ultraviolet glow, a phenomenon so unexpected and grand it has been nicknamed the Phoenix Aurora for its ability to appear in a place where such things were thought to be impossible. The discovery of this Martian marvel is a testament to our growing presence on and around the red planet. It wasn't a telescope on Earth that spotted it, but NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, which is specifically designed to study the Martian atmosphere. As MAVEN studied how solar wind strips away the Martian air, its ultraviolet instrument detected a faint but widespread glow across the entire night side of the planet. This was no ordinary aurora, it was a seamless global phenomenon, utterly unlike the concentrated ribbons of light we see at Earth's poles. The Phoenix Aurora doesn't dance, it simply is a permanent, gentle veil of energy draped across the world. The mechanism behind this impossible light show is as fascinating as the discovery itself. Billions of years ago, Mars likely had a global magnetic field like Earth's, generated by a dynamo in its molten core. But as the planet cooled and its core solidified, that global field collapsed and faded away. What remains today is a haunting fossil record of that ancient field. Pockets of intensely magnetized crust, locked into the ancient volcanic rock like scattered magnets buried all across the planet. These magnetic anomalies create localized, umbrella-like magnetic fields that punch up through the thin Martian atmosphere. When a torrent of charged particles from a solar storm hits Mars, these magnetic umbrellas act as conduits, guiding the particles down into the atmosphere across almost the entire planet, not just at the poles. The solar particles then collide with atoms and molecules in the thin Martian air, primarily carbon dioxide and oxygen, causing them to fluoresce in ultraviolet light. It's a completely different kind of auroral engine, one that uses the corpse of a dead magnetic field to paint the entire sky. This discovery fundamentally rewrites our understanding of both Mars and planetary science as a whole. We used to think a strong, global dipole magnetic field was a prerequisite for significant auroral activity. The Phoenix Aurora proves that isn't true. A planet can have a patchwork, broken magnetic field and still put on a light show that, while invisible to the human eye, is every bit as magnificent in its own way. It reveals a layer of atmospheric complexity we never anticipated, showing how solar wind can interact directly with a planet's atmosphere in the absence of a global shield. This has profound implications for our search for life beyond our solar system. We often categorize habitable worlds as those with Earth-like magnetic protection, but the Phoenix Aurora suggests that even planets without this protection might still have ways of interacting with their star that could potentially preserve their atmospheres or create unique chemical environments. The phenomenon also serves as a constant, real-time display of atmospheric loss. Every time the Phoenix Aurora ignites, it marks the spot where solar energy is flooding into the Martian atmosphere, energizing particles and giving them the velocity to escape into space. By studying the intensity and distribution of this glow, scientists can literally watch the last breaths of the Martian atmosphere being slowly stripped away by the solar wind, a process that transformed Mars from a warm, wet world potentially capable of nurturing life into the cold, dry desert it is today. The beautiful, haunting glow of the Phoenix is therefore also a funeral shroud, a luminous marker of a world's demise. It stands as a stunning reminder that the universe is full of surprises, capable of creating profound beauty even in the midst of loss, and challenging our most fundamental assumptions about how planets live and die. Now we turn to a cosmic engine that seems to be operating in reverse, a singularity that defies the standard rules of celestial mechanics. This is the story of a backwards black hole, a supermassive object whose spin is misaligned with or even directly opposed to the rotation of its surrounding accretion disk. Imagine a colossal drain, but one where the water is swirling in one direction while the drain itself is spinning the opposite way. According to our models, this configuration should be violently unstable, a transient state that physics would quickly correct. Yet, we have found one, and its continued existence is forcing us to rewrite the rules of how these cosmic monsters grow and evolve. The spin of a black hole and the rotation of its accretion disk are fundamentally linked. As material from the disk spirals inward, it doesn't just feed the black hole. It also transfers its angular momentum, like a rolling snowball adding its spin to the larger mass it joins. Over time, this process naturally forces the black hole's spin axis and the disk's rotational plane to align, creating a stable, efficient feeding system. A counter-rotating system is the astrophysical equivalent of trying to pour water into a moving glass by throwing it backwards. It's messy, inefficient, and tremendously turbulent. The friction and magnetic stresses at the boundary between the backwards spinning black hole and the forward spinning disk should create immense turbulence, generating powerful shocks that would either rapidly slow the black hole's spin or tear the disk apart, forcing a realignment on a relatively short cosmic timescale. The discovery of such a system, therefore, is like finding a spinning top that has been perpetually falling over yet never actually hits the ground. It points to a recent, violent, and chaotic event that overpowered this natural tendency for alignment. The most plausible explanation is a galactic merger of epic proportions. Picture two galaxies, each with its own supermassive black hole at the center, slowly colliding and combining over billions of years. If these two black holes had accretion disks that were spinning in different directions relative to their orbital plane, their eventual merger would create a chaotic mess. When the two black holes finally coalesced, the resulting gravitational wave recoil could have kicked the newborn black hole, sending it tumbling and leaving it with a spin axis that is completely misaligned with the new, larger accretion disk formed from the combined gas of both galaxies. The persistence of this backward state tells us two incredible things. First, it suggests that the merger was both recent and incredibly gas-rich. There must be a vast amount of fresh material continually falling in to constantly rebuild and maintain the misaligned disk against the forces trying to tear it down. We are witnessing the aftermath of the collision in real time, a brief window of cosmic violence that we were lucky enough to catch before equilibrium is restored. Second, it reveals that the environments around supermassive black holes are far more complex and dynamic than our simple, stable models assumed. This turbulence has dramatic consequences. A misaligned disk can create wildly asymmetric jets and outflows, and the intense friction can heat the accretion disk to much higher temperatures, altering the entire spectrum of radiation that the active galactic nucleus emits. This means that a backwards black hole doesn't just look different on paper, it behaves differently, shining in a unique way that we are only beginning to understand. This bizarre object is more than a curiosity. It is a direct snapshot of the chaotic process of galaxy growth. Most large galaxies, including our own Milky Way, were built through a history of such mergers. The existence of a backwards black hole provides the first direct observational evidence that these mergers can leave their central engines in a profoundly disturbed state, a testament to the violent forces that have shaped the universe we see today. It shows us that the cosmos is not always a place of orderly motion, but often a chaotic arena where the rules are written in the aftermath of catastrophe, and where equilibrium is a prize won only after a long and turbulent struggle. What if the most violent engine in the universe could also be a nursery? This paradox lies at the heart of our 29th oddity, a newly discovered cosmic hybrid so baffling it seems to break the fundamental rules of galactic life and death. Astronomers have dubbed it the cold quasar, and it represents a phase of existence that our models claimed was impossible. A galaxy hosting a ravenous, matter-devouring supermassive black hole while simultaneously giving birth to thousands of new stars. It is a place of both furious creation and apocalyptic destruction, a celestial Jekyll and Hyde that is forcing us to completely rethink how galaxies evolve. To understand why this is so revolutionary, we need to look at the standard galactic life cycle. For decades, the story went like this. A young galaxy is a bustling stellar factory, rich with cold gas that condenses to form new stars. At some point, if conditions are right, a supermassive black hole at its center begins to feed, growing into an active galactic nucleus or a quasar. As this black hole feasts, it becomes incredibly powerful, blasting out immense amounts of energy and radiation. This radiation heats up the surrounding gas, preventing it from cooling and collapsing into new stars. Furthermore, the quasar can drive powerful winds that physically blow the star-forming gas right out of the galaxy. This process, known as quenching, is the predicted death knell for star formation. The quasar essentially sterilizes its own home, shutting down the very process that might have fed it in the future and leaving behind a silent, red and dead galaxy. The two states, furious star birth and furious black hole growth, were thought to be mutually exclusive, separated by a brief, turbulent transition. The cold quasar shatters this orderly timeline. Here, we see a supermassive black hole in the full, blazing glory of its quasar phase, pumping out enough radiation to outshine its entire host galaxy. But instead of a hot, dissipating gas cloud, the galaxy is still brimming with enormous reservoirs of cold, dense molecular gas, the very raw material for building stars. And indeed, observations show that star formation is proceeding at a rampant pace, with hundreds of new suns igniting every year. It's as if a volcano were erupting with catastrophic force at the center of a city, yet all the while, the people outside are calmly laying new foundations and building new houses, completely unperturbed by the apocalypse next door. This isn't a brief moment of overlap, it's a sustained state of coexistence that our theories struggle to explain. How can such an environment possibly persist? How can cold gas survive the infernal glare of a quasar? The leading theory involves a cosmic game of hide and seek on an epic scale. The immense clouds of star-forming gas and dust may not be evenly distributed throughout the galaxy. Instead, they could be clustered in massive, dense clumps far from the galactic center, shielded from the quasar's most direct and intense radiation. The dust within these clouds is incredibly effective at absorbing the quasar's high-energy light and re-radiating it as lower-energy infrared light, effectively acting as a cosmic sunscreen for the baby stars forming within. Alternatively, the sheer quantity of gas might be so overwhelming that even a quasar's tremendous energy output can only heat and disperse a fraction of it at a time. The black hole is trying to blow out the candle, but the galaxy has provided a hurricane of new wax. The discovery of cold quasars suggests that the quenching of a galaxy is not the swift, decisive event we once imagined. It may be a long, drawn-out, and inefficient process full of fits and starts. This revelation has profound implications for our understanding of cosmic history. For a long time, the observed population of massive, dead galaxies in the modern universe was a puzzle. How did they form their stars and then shut down so quickly? Cold quasars may be the missing link, representing that extended and chaotic transitional period where a galaxy is trying to die, but its own inherent richness won't let it. It is a phase of prolonged internal conflict, a battle between the creative force of gravity and the destructive fury of the black hole. And for now, in these strange objects, it appears to be a stalemate. And now, we reach the final stop on our tour of cosmic oddities, a journey that brings us back to our own solar system, to the frozen, dark frontier where the sun's influence wanes and the clues to a massive secret are written in the slow, silent orbits of ancient ice. Our 30th and final oddity isn't a galaxy or a nebula, but a relatively tiny worldlet whose improbable path through the void makes it one of the most compelling celestial detectives in our quest to understand our own home. This is the story of the extreme trans-Neptunian object nicknamed the Goblin, and how its lonely journey is whispering to us of a giant, unseen world, a potential ninth planet lurking in the perpetual twilight. Discovered in 2015 by astronomers with the Outer Solar System Origin Survey, the Goblin, officially designated 2015 TG 387, earned its spooky nickname from the letters in its provisional designation and the fact it was first spotted near Halloween. But its true eeriness lies in its orbit, a path so extraordinarily elongated it seems almost fictional. This small, likely icy body, no more than 300 kilometers across, spends the overwhelming majority of its existence in a state of profound isolation. Its orbit takes it on a staggering journey that lasts 40,000 years. At its closest approach to the Sun, its perihelion, it still remains twice as far out as Neptune. But then it swings outward, receding into the deep freeze to a distance of over 2,300 astronomical units. At that incredible aphelion, the Sun would be little more than a bright star in its sky, and a single year on this world would span a period longer than all of recorded human civilization. The sheer extremity of this orbit is the first clue that something is amiss in the outer solar system. Objects don't just naturally fall into such stretched-out paths on their own. They need a gravitational nudge, a repeated and powerful influence that herds them into a specific orbital configuration. The Goblin is not alone in this. It is part of a small but statistically significant group of extreme trans-Neptunian objects whose orbits share a peculiar commonality. Their points of closest approach to the Sun are clustered together in physical space, and their highly elliptical orbits are tilted in a similar direction. This is the equivalent of scattering 100 compass needles on a table and finding they all point not just north but 20 degrees northwest. The probability of this happening by random chance is astronomically low, less than 0.001%. This orbital synchronicity is a giant arrow pointing to an external force, a massive something whose gravity is organizing the dance of these distant ice dwarfs. This is where the hypothesis of Planet 9 enters the picture. The Goblin's orbit is one of the cleanest and most persuasive pieces of evidence for its existence. The proposed Planet 9, with a mass 5 to 10 times that of Earth, would orbit the Sun hundreds of times farther out than we do. Its immense gravitational pull, exerted over billions of years, would act as a shepherd for objects like the Goblin. The mathematics are elegant and compelling. The long-term gravitational influence of such a distant planet would naturally sculpt the orbits of these smaller bodies, pushing their perihelia away from Planet 9's own path and clustering their orbital angles just as we observe. The Goblin in this model is not a random wanderer. It is a tracer bullet, its path etched by the persistent, rhythmic tug of a distant, unseen giant. Its orbit is a fossil record of a gravitational interaction, a permanent signature of Planet 9's influence. What makes the Goblin such a crucial witness compared to other objects in this group is its perihelion distance. It never comes close enough to the giant planets, particularly Neptune, to have had its orbit significantly altered by them. This isolation is vital. It means the peculiarities of its path cannot be easily explained away by past encounters with known planets. Its bizarre orbit is pristine, uncontaminated by the messy gravitational interactions of the solar system's middle suburbs. It is a pure signal from the farthest reaches, a clean data point that points unequivocally to a new, massive perturbing body. It acts as a gravitational Rosetta Stone, allowing astronomers to run sophisticated simulations that can actually constrain the possible mass and orbit of the hypothetical planet 9 itself. By studying the Goblin's path, we can essentially triangulate the position of its hidden master. Of course, the scientific process demands skepticism, and alternative explanations have been proposed. Some researchers suggest that the collective gravity of many smaller, uncharted objects in the Kuiper belt could, in theory, produce the same shepherding effect. Others have posited that a single, ancient close pass by a rogue star in the Sun's birth cluster could have yanked these objects into their strange orbits billions of years ago. Yet, these explanations often struggle to reproduce the precise and sustained orbital clustering we see, especially in objects like the Goblin with their high perihelion orbits that are immune to further meddling from Neptune. The Planet 9 hypothesis, while still a hypothesis, remains the most robust and elegant solution that fits all the data. The search for this frozen giant, or whatever is causing these gravitational whispers, is one of the great astronomical quests of our time. Telescopes like Subaru on Mauna Kea are tirelessly scanning the vast proposed orbital path, looking for the faint, slow-moving glint of reflected sunlight that would confirm the theory. The discovery of each new object like the Goblin further refines the search area, tightening the net around this cosmic phantom. Whether it is a true planet, a primordial black hole, or something even stranger, the story told by the Goblin is a powerful reminder that our solar system is not a static museum piece. It is a dynamic, evolving system with a history of violence and rearrangement, and its farthest depths may still hold secrets as large as planets, waiting for the right clue, the right orbit to reveal them. This small, distant Goblin has become a guide, pointing our telescopes and our imaginations toward the next great discovery waiting in the dark. And so our journey through the cosmos's cabinet of curiosities comes to a close for now. We've ventured from the invisible tempest of a dark matter hurricane, silently sweeping through our solar system, to the impossible, geometric perfection of the Red Rectangle Nebula. We've witnessed stars being catapulted from the galaxy by a monstrous black hole, and pondered the existence of a phantom planet lurking in our own celestial backyard. We've stood in awe of the impossible, from a galaxy made of 99% nothing but dark matter to a single, universe-spanning ghost particle that opened an entirely new window onto the most violent engines of creation. Each one of these 30 discoveries, from the profoundly cold great nothing of the Boötes void to the rhythmic, ticking heartbeat of a feeding black hole, serves as a powerful testament to one simple, staggering fact. The universe is not only stranger than we imagine, it is stranger than we can imagine. What unites these bizarre phenomena is not just their capacity to baffle and astonish, but their incredible power to push the entire enterprise of science forward. A mystery is not a dead end, it is an invitation. The confounding spin of a backwards black hole forces us to refine our understanding of gravity and galactic collisions. The impossible existence of an ancient, fully formed galaxy like GNZ 11 challenges our most fundamental timelines for cosmic evolution. Even the fleeting, controversial passage of an object like Oumuamua, whether it's a nitrogen iceberg or something more, has spawned an entirely new field of study dedicated to interstellar interlopers. Every single oddity on this list is a direct challenge to our current models, a beautiful puzzle that demands a new piece of physics, a sharper telescope, or a more brilliant theory to solve it. They are the growing pains of our understanding, the moments where the universe looks us squarely in the eye and says, "You haven't figured it all out yet." This relentless, humbling, and exhilarating process is what science is truly about. It's a perpetual state of wonder, a recognition that for every question we answer, the cosmos presents us with 10 more, each more profound than the last. The map of human knowledge is still mostly terra incognita, and these 30 oddities are the faint, tantalizing outlines of undiscovered continents waiting to be explored. They remind us that curiosity is our most valuable compass, guiding us not toward a final destination of complete understanding, but on an endless, wondrous voyage of discovery. Now we turn the conversation over to you. Which of these cosmic marvels reshaped your perception of reality the most? Was it the haunting idea of a dark matter hurricane passing through you right now, completely undetected? The chilling possibility that the great cold spot is a bruise from a collision with another universe, or the terrifying elegance of a black widow pulsar slowly vaporizing its stellar companion to fuel its own spin. Let us know in the comments below which oddity captured your imagination and why. If you enjoyed this deep dive into the edges of known space, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the universe's greatest mysteries. The cosmos is vast, strange, and full of secrets waiting to be uncovered. Join us as we continue